Welcome, and thank you for joining me here on The Sleepy Scientist, a quiet corner of the universe where science drifts slowly, softly, and just a little bit dreamily. If you're listening as you unwind for the night, then settle in, get comfortable, and let your mind float outward, past the planets and moons, toward a place where sunlight fades into the endless dark. Tonight, we're heading beyond Neptune, into the vast frozen frontier known as the Kuiper Belt, a place so distant that even light, travelling at almost 300,000 kilometers per second, takes nearly 6 hours to get there. Before we drift too far into the cold, I'd love to know, where in the world are you watching from? A quiet room, a busy city, maybe somewhere under a real starry sky? Drop a comment and let me know. I always enjoy seeing where these sleepy journeys reach. And if you enjoy these slow explorations of space and science, please do give this video a like and subscribe to The Sleepy Scientist. To everyone who's already part of this calm little community, thank you sincerely for being here. You keep the stars shining. And if you haven't yet, please tap the notification bell so you don't miss the next journey through time, atoms, or galaxies. I do hope this video isn't so interesting that it keeps you awake, though if it does, at least you'll drift off a little wiser than before. Now, as the night deepens and the hum of the world fades, here's a thought to start our journey. What secrets lie hidden in the frozen shadows beyond Neptune? In that silent sea where the sun is just another star, the Kuiper Belt. It sounds almost poetic, doesn't it? Like a ring of frost circling the edge of imagination itself. But this place is no myth. It's real, and it holds some of the oldest, most untouched relics of the solar system's creation. Out past the orbit of Neptune, some 40 to 55 times farther from the Sun than Earth, lies a vast region filled with ice, rock, and ancient dust, the Kuiper Belt. It's a cosmic attic, storing leftovers from the dawn of planetary time. While the inner solar system was busy building planets, this distant region remained cold, quiet, and largely undisturbed, a frozen archive preserving what the early nebula once was. Imagine sunlight that takes half a day to arrive. Imagine shadows so long that one side of a mountain might spend a century in darkness. Here, the temperatures hover near absolute zero, and the pace of change slows to a whisper. Worlds here do not rush, they drift, they turn, they dream. Within this quiet expanse live thousands of icy bodies, dwarf planets like Pluto, Haumea, Makemake, and Eris, frozen pebbles and mountain-sized boulders, even binary worlds locked together in eternal orbit. Every one of them holds clues to how the solar system formed and to why it looks the way it does today. The Kuiper Belt isn't just the solar system's edge, it's a bridge between what we know and what we've barely begun to imagine. Beyond it lies the scattered disk, and farther still, the mysterious Oort cloud, the icy halo that might cradle the seeds of comets. In this video, we'll journey through this frozen realm. We'll explore how it formed, how Neptune's slow dance sculpted its shape, and what secrets its icy residents hide beneath their distant sunlight. We'll meet Pluto and Charon, learn how comets are born, and discover why the Kuiper Belt may be one of the most important archives in the solar system, a cosmic time capsule older than Earth itself. So, take a slow breath, close your eyes if you like, and let your thoughts drift outward, past the warmth of the sun, through the stillness of the giant planets, until only the deep cold remains. Welcome to the frozen Kuiper Belt, where the solar system remembers its earliest dreams. Long before there were planets, moons, or comets, there was dust, just endless swirling dust. The solar system began as a cloud of gas and fine particles. The remains of earlier stars that had lived exploded and scattered their elements into space. Slowly, gravity drew that cloud inward, flattening it into a great rotating disk, a cosmic pancake of starlight and potential. Near the centre, where the newborn sun burned fiercely, temperatures soared high enough to vaporize most ices, leaving behind rock and metal. But farther out beyond the warmth, the cold took over. Here, in the deep freeze of space, ices could survive, and the building blocks of distant worlds began to form. Scientists call this invisible dividing line the ice line, or frost line. Inside it, everything is warm and volatile materials like water, carbon dioxide, and methane are vaporized. Outside it, temperatures drop so low that those same gases freeze solid, coating grains of dust with layers of frost. These icy grains stick together more easily than bare rock, like snowflakes merging into slush. It's beyond this frost line, tens of times farther from the sun than Earth, that the story of the Kuiper Belt truly begins. Out in that region, time worked differently. Clocks didn't tick in minutes or hours, but in millions of years. The gas and dust moved slowly, and collisions between particles were gentle rather than violent. Tiny grains bumped, clung, and gradually grew into larger clumps. Over time, these became pebbles, then boulders, then bodies kilometers across. Astronomers call this process accretion, and though it sounds technical, it's really just cosmic snowballing, gravity's way of turning grains into globes. Yet the pace of growth in the far reaches was glacial. The farther you were from the sun, the less material there was to work with, and the longer it took for objects to collide and merge. Think of it like trying to build a snowman in a field where each flake falls several kilometers apart. The result was a population of half-built worlds, too small to become planets, too numerous to vanish entirely. These became the Kuiper Belt's icy residents, the frozen leftovers of creation. In those early days, the outer solar system was likely far busier than it is now. Billions upon billions of planetesimals orbited the young sun, filling space with motion and possibility. But over time, many of these small worlds were either ejected by the gravitational tug of the giant planets, or sent spiraling inward to meet fiery ends. What remained was a fraction of the original crowd, a thin, ghostly remnant of what once was. Today, the Kuiper Belt we observe is a shimmering frost ring circling the sun, a sparse echo of its once dense youth. Still, what survived tells an incredible story. The objects out there are ancient, untouched, for over 4 billion years. Because they've stayed so cold and so far away, they've barely changed since the solar system's earliest days. Each one is a time capsule, preserving chemistry and structure from a time when Earth itself was only dust and dreams. Studying them is like opening a freezer full of ingredients left over from the first recipe for planets. The formation of these worlds likely involved more than simple collisions. Recent research points to a process called pebble accretion, where small particles drift slowly through the gas of the young solar system and stick to larger ones with surprising efficiency. Instead of countless tiny impacts, this creates a smoother, faster growth, like rolling a snowball downhill through freshly fallen powder. But even pebble accretion has its limits. Beyond a certain distance from the sun, the gas in the disk thins, the pebbles drift too slowly, and growth nearly stops. That's where the Kuiper Belt draws its boundary, the place where nature ran out of time and material to finish building planets. The result is a kind of cosmic construction site frozen mid-project. Some bodies became round under their own gravity, forming dwarf planets like Pluto and Eris. Others remained irregular chunks of ice and rock, never large enough to smooth out. All of them orbit the sun together, faint and cold, as reminders of a process that mostly ended long ago. If you could stand on one of these ancient worlds, not that you'd want to, since the temperature hovers around -200 degrees Celsius, you'd see a black sky scattered with distant stars and one small, pale sun. It would be so dim that your shadow might barely appear. Around you, the landscape would be silent, a mix of rock and frozen methane, shaped only by the slow fall of micrometeorites and the faint touch of sunlight. And if you waited long enough, perhaps several million years, you might finally see another object drift faintly across the horizon. Because while the Kuiper belt contains countless bodies, they are separated by enormous distances. On average, each one is about as far from its nearest neighbour as Earth is from the Moon, and often much farther. Astronomers like to joke that it's the least social neighbourhood in the solar system. The planetesimals may want to meet up, but everyone lives about 500 million kilometres apart, and yet, even in all that emptiness, gravity holds a delicate balance. Those frozen relics continue their slow orbits, circling the sun in silence, whispering stories of a time before time, when the solar system was young, and the line between chaos and creation was drawn in frost. Neptune wasn't always where it is today. In the early solar system, the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not sit neatly in their modern positions. They moved, slowly, gracefully, but with enormous consequence. This process, called planetary migration, reshaped the solar system's architecture like a slow-motion dance that lasted hundreds of millions of years. And at the far edge of that cosmic ballroom, the Kuiper belt still bears the footprints of Neptune's gentle yet powerful steps. To understand migration, imagine the early solar system as a crowded disk of gas, dust and ice, swirling around the newborn sun. The giant planets were still forming, pulling in material and jostling for position. As they interacted gravitationally with the leftover debris, tiny exchanges of momentum began to shift their orbits. Each encounter between a planet and a smaller body was like a subtle tug on a celestial rope. One body would move inward slightly, the other outward. A single tug changes almost nothing, but over millions upon millions of such encounters, the effect adds up. Neptune, the outermost of the gas giants, was particularly influenced by this gravitational give and take. Billions of icy planetesimals drifted beyond it, and as Neptune scattered them, it slowly moved outward, like a skater gliding backward by pushing pebbles forward across the ice. Jupiter, the most massive of the planets, moved slightly inward, while Neptune crept outward, expanding the solar system's edges. This subtle reshuffling set the stage for one of the most elegant gravitational phenomena in the cosmos: orbital resonances. An orbital resonance happens when two bodies orbit the Sun in a synchronized rhythm. It's as if the universe has a metronome, ticking out a pattern of cosmic timing. For example, if Neptune completes 2 orbits around the Sun for every 3 made by a smaller object, that object is said to be in a 3-to-2 resonance with Neptune. Each time the two align, their gravitational tugs occur in the same positions relative to one another, keeping the smaller body's orbit stable, sometimes for billions of years. This is not a coincidence, it's gravity's version of harmony. Just as certain musical notes sound pleasant together because their vibrations align in neat ratios, certain orbital ratios between planets and smaller bodies can create long-term stability. Too far from resonance, and orbits become chaotic, shifting over time. But locked into resonance, even tiny worlds can survive the gravitational pull of giants. Neptune's outward migration swept up many of the icy bodies that once orbited freely. As it moved, it captured some of them into resonances, dragging them along like dancers link arm in arm. Others were flung outward or inward, scattered into eccentric paths. This process sculpted the Kuiper belt into the structure we see today, a region of distinct families, resonant objects, scattered objects, and those that remain in quieter, more circular orbits known as the cold classical belt. The most famous of these resonant dancers are the so-called Plutinos, named after their best-known member Pluto. Plutinos share a 3-to-2 resonance with Neptune, meaning that for every 3 times they orbit the Sun, Neptune completes 2. This rhythm keeps them from ever coming too close to the giant planet. Even though Pluto's orbit crosses Neptune's path on paper, the two are locked in a gravitational waltz that ensures they never collide. Every time Pluto reaches the point in its orbit where it comes nearest to Neptune, the gas giant is safely elsewhere, far across the solar system. It's an elegant choreography, 2 worlds perpetually out of sync yet perfectly in tune. The same principle governs many other Kuiper belt objects like the 2 Tinos, which orbit in a 2-to-1 resonance, and others in more complex fractional rhythms. Each resonance is like a note in a frozen symphony, each object keeping time to Neptune's invisible beat. Over time, this cosmic music carved the belt into distinct populations. The resonant groups mark Neptune's long outward migration path, like footprints left in snow. Farther out, where Neptune's gravitational reach weakens, the orbits become more random and scattered. Some of these bodies were ejected entirely from the solar system, cast into the interstellar dark. Others were sent inward to eventually become centaurs or comets, messengers from the outer cold who occasionally pay the Sun a visit. It's remarkable to think that much of the Kuiper belt structure, its gaps, clusters, and resonant patterns, was shaped by movements so slow they make continental drift look hasty. From our perspective, Neptune seems steady, a blue dot unmoving among the stars. But its outward stroll over hundreds of millions of years left an indelible signature, frozen into the arrangement of worlds that orbit beyond it. Today, when astronomers map the Kuiper belt, they find order amid the cold. The resonant objects form patterns that trace Neptune's invisible influence, like ripples spreading across a frozen lake. Each one confirms that the solar system was never static. It evolved, breathed, and rearranged itself, sculpted by the quiet persistence of gravity. If the Kuiper belt is a fossil, Neptune is the artist who shaped it. Its long waltz outward left behind the architecture of a cosmic dance floor, one that still moves in perfect time long after the music began to fade. And so, when you look at the distant blue planet through a telescope, remember, it is not just a cold world circling the Sun. It is the conductor of a frozen orchestra, keeping time across billions of kilometers, guiding worlds that it will never touch, yet forever influence. Neptune may have moved the furniture long ago, but the room still holds its rhythm, a quiet gravitational melody echoing through the dark. The Kuiper belt might seem like one endless sea of frozen rocks drifting quietly through space, but in reality, it's a world of distinct neighborhoods. Not all of its residents behave the same way, or even look alike. Some move in tidy circular paths, while others hurtle through space on steep tilted orbits that carry them far above and below the solar system's plane. Some are calm and ancient, others wild and restless. To understand the Kuiper belt, you have to see it not as one continuous band, but as a collection of families, each shaped by its own history and temperament. Astronomers often speak of 2 main branches of the Kuiper belt, the cold classicals and the hot populations. The words cold and hot here don't refer to temperature. Everything out there is frozen well below -200 degrees Celsius, but to orbital motion. The cold classical objects follow smooth low-inclination orbits that stay close to the plane of the solar system, as if they're calmly tracing a gentle ring around the Sun. The hot populations, in contrast, have more chaotic paths. Their orbits are tilted, stretched, and eccentric, like dancers who've broken away from the formation. The cold classicals are the quiet heart of the Kuiper belt. They tend to have circular orbits, move in neat harmony, and show a deep reddish hue when viewed through telescopes. That colour tells a chemical story. Their surfaces are rich in complex organic molecules called tholins, formed when ultraviolet sunlight slowly alters frozen methane and nitrogen over billions of years. Many of these objects are also found in binary pairs, two bodies orbiting one another, locked in a slow, eternal spin. That so many binaries have survived suggests this region has been calm since the dawn of the solar system. If collisions had been frequent or violent, most of these delicate partnerships would have been shattered long ago. In contrast, the dynamically hot populations are more like the Kuiper Belt's wanderers, restless, tilted, and stirred up by gravitational disturbances. Their orbits show that they've been tossed around, possibly by Neptune's outward migration, or by ancient gravitational encounters with other large bodies. These hot populations come in several varieties: resonant objects locked in rhythm with Neptune's orbit, scattered objects with stretched, eccentric paths, and a more mysterious class known as detached objects, worlds that seem to orbit too far away to be influenced by Neptune directly. The scattered disk, as its name suggests, is filled with objects that have been flung into wild trajectories. These bodies can travel from near Neptune's orbit to regions dozens of astronomical units farther out, tracing long, elongated loops around the Sun. The reason they're called scattered is that they were, long ago, literally scattered by gravitational encounters with Neptune, and perhaps Uranus. When one of these giant planets passed close to a smaller icy body, it gave it a tug, changing its orbit dramatically. Some were hurled inward to become comets, others outward into long-distant paths. A few ended up marooned between the Kuiper Belt and the Oort cloud, where they still drift today. Detached objects, on the other hand, seem to have slipped Neptune's grasp entirely. They travel on distant, stable orbits that never bring them close enough to the planet to be influenced by it. Their closest approach to the Sun, called their perihelion, is far beyond Neptune's orbit. Perihelion simply means the point where an object comes nearest to the Sun during its orbit, while aphelion marks the farthest point. For detached objects, that nearest point is still unimaginably far away, so far that Neptune's gravity barely stirs them at all. How they got there remains one of the Kuiper Belt's lingering mysteries. Some scientists suspect that passing stars, or perhaps even an undiscovered massive planet in the distant dark, may have shaped their paths long ago. These distinctions, cold classicals, hot populations, scattered and detached objects, aren't just labels. They tell a story about time and trauma, about peace and disruption. The cold classicals likely formed right where they are, and have remained undisturbed ever since. They're fossils of the original solar system, their chemistry and structure almost pristine. The hot and scattered populations, however, are survivors of chaos, evidence that the outer solar system once pulsed with far more energy and instability than it does today. Their surfaces, too, reflect these different lives. Cold classical objects with their rich, reddish tholins are coated in the residue of cosmic radiation and solar light, a patina that deepens with time. The hot populations, on the other hand, display more varied colours, from neutral grey to bright red, depending on how their surfaces were altered by impacts and heating during their long wandering journeys. Each orbit is like a biography, telling scientists how long an object has been exposed, how often it's collided, and how much it's been baked or blasted by distant sunlight. You might think of the Kuiper Belt structure like a frozen landscape after a storm. The cold classicals are the neat snowdrifts, soft, untouched and smooth, lying quietly where they first fell. The scattered and hot populations are more like wind-tossed powder, shaped by gusts and turbulence, full of motion and irregularity. Both are beautiful in their own way, one a record of stillness, the other a record of change. And the boundaries between these families aren't always strict. Some objects blur the lines, occupying intermediate orbits that hint at shared origins or long histories of migration. The more we map and measure them, the more intricate the Kuiper belt structure becomes. It's not a simple ring of debris, but a complex layered relic of planetary formation, a record written in frozen orbits. Astronomers have identified thousands of Kuiper belt objects, yet they believe this represents only a fraction of what's really out there. The faintness of these icy bodies makes them difficult to spot, even with modern telescopes. Most are no more than 100 kilometers across, reflecting only a tiny sliver of sunlight. But each new discovery adds a note to the symphony of structure, helping to reveal how the belt came to be the way it is today. Every family within the Kuiper belt adds its own voice to that cosmic harmony. The cold classicals whisper of stillness and preservation. The hot populations speak of turbulence and migration. The scattered disk hums with motion and memory, while the detached objects keep their quiet secrets in the deep dark. Together, they make the Kuiper belt not just a boundary of the solar system, but a living record of its evolution, a frozen archive where time itself seems to move at the speed of ice. If the Kuiper belt were a frozen kingdom, then its royalty would be the dwarf planets, icy monarchs ruling over a realm of smaller, humbler bodies. Each one is unique, with its own character, chemistry, and curious quirks. They share a common birthplace in the cold, but their stories diverge wildly. In this far-off frontier, size isn't everything. It's the diversity of worlds that makes this icy court so fascinating. At the head of this frosty lineup stands Pluto, once considered the 9th planet, now proudly the most famous dwarf planet in the solar system. Discovered in 1930, Pluto is about 2/3 the diameter of Earth's moon and has a surprisingly dynamic surface. When the New Horizons spacecraft flew past in 2015, it revealed a world full of unexpected variety. Plains of nitrogen ice, towering water ice mountains, and vast stretches of ancient cratered terrain. One of its most striking features, the heart-shaped region known as Tombor Regio, became an instant icon. Half a frozen plain called Sputnik Planitia, the other half a patchwork of hills and frost. Pluto's thin atmosphere, made mostly of nitrogen with traces of methane, is seasonal and delicate. As Pluto moves along its long elliptical orbit, one that takes it from roughly 4.5 billion kilometers to 7.5 billion kilometers from the Sun, it alternately warms and cools. When closer to the Sun, the surface ices sublimate, forming a tenuous atmosphere. Farther away, that atmosphere freezes again and falls back as snow. In Pluto's world, entire atmospheres come and go like winter frost on a window. Orbiting Pluto is its large moon, Charon, so large in fact that the two are often described as a binary system, rather than a planet and its satellite. Charon is about half Pluto's size, and together they orbit a common point in space that lies between them. It's a cosmic dance where neither partner truly leads. The two worlds are tidally locked, each keeping the same face toward the other, so from Pluto's surface Charon never rises or sets. Their gravitational bond creates a tidal relationship that has likely shaped both their surfaces and their internal structures. The pair is like two dancers in perfect balance, moving together through the darkness in silent harmony. Not all of Pluto's companions are so well behaved. Next in the royal court is Eris, slightly smaller in diameter but more massive than Pluto, making it the true heavyweight of the Kuiper belt. Eris orbits even farther from the Sun, in a highly elongated path that takes it nearly twice as far out as Pluto at its most distant. It's an icy world with a reflective surface brighter than fresh snow, likely covered in frozen nitrogen and methane. When Eris was discovered in 2005, its size caused such a stir that astronomers were forced to reconsider what it really means to be a planet. That debate led to the creation of the dwarf planet category, and to Pluto's controversial reclassification. Eris also has a tiny moon named Dysnomia, which helps scientists measure its mass and density. Despite its distance, Eris reflects so much sunlight that it gleams in telescopes like a faraway jewel. It is, in every sense, the distant queen of the outer solar system, small, cold, and dazzlingly aloof. Haumea, by contrast, is the eccentric cousin, spinning so fast that it's stretched into an elongated, football-like shape. It completes one rotation in under 4 hours, making it one of the fastest spinning large bodies in the solar system. This rapid spin has likely caused its odd form, and may have even thrown off fragments that became its moons, and a faint ring system that circles its equator. Haumea's surface is coated mainly in water ice, giving it a bright sheen, but beneath that icy crust may lie a rocky core. Discovered in the early 2000s, Haumea's family of moons and its ring make it one of the most distinctive members of the Kuiper Belt's elite. It's a reminder that even in the quiet, cold, motion and chaos still shape worlds. Makemake, another of the Kuiper Belt's bright monarchs, is roughly 2/3 the size of Pluto and covered in frozen methane and ethane. It lacks the dramatic topography of Pluto's surface, but its chemistry is rich and colourful. Methane on its surface slowly breaks down under solar radiation, forming reddish organic compounds that tint the world with a soft blush. For a long time, Makemake was thought to have no moons, but in 2016 astronomers discovered a small one, nicknamed MK2, quietly orbiting its host. Makemake's reflective surface and chemical makeup suggest that it too experiences subtle atmospheric changes when sunlight reaches it, though far less dramatic than Pluto's seasonal breathing. Then there's Quaoar, a relatively modest dwarf planet named after a creation deity from Tongva mythology. Discovered in 2002, Quaoar surprised astronomers in 2023 when it was found to have a ring, something few expected at that distance. Normally, a ring that close to a small body should collapse into a moon, but Quaoar's ring sits just beyond the theoretical Roche limit, where tidal forces would normally prevent such a structure from surviving. How it persists remains a mystery, but it shows that even small, frozen worlds can break the rules in surprising ways. Quaoar's surface appears to be rich in water ice, and possibly methane, giving it a bright, icy appearance and linking it to the other members of this frozen family. Each of these dwarf planets has its own distinct personality. Pluto, with its dynamic geology and atmosphere, feels almost alive. Eris is remote and austere, shining like an icy diamond in the dark. Haumea is restless, spinning itself into an ellipsoid and flinging bits of itself into orbit. Makemake glows with the chemistry of slow, frozen sunlight, while Quaoar quietly defies gravitational logic with its delicate ring. Together, they remind us that even in the farthest corners of the solar system, variety thrives. What makes this diversity so intriguing is that all these worlds formed from the same raw ingredients: ice, rock, and dust. They've all spent billions of years in deep freeze, yet their appearances and behaviours are dramatically different. Subtle differences in size, spin, composition and sunlight exposure have sculpted them into distinct forms. The Kuiper Belt may be cold, but it's anything but uniform. In the end, these frozen monarchs are less a single family than a gallery of possibilities. Each shows what can happen when time, gravity and chemistry take their slow course at the edge of the sun's domain. They are the same ingredients, but different recipes, each one baked in the same cosmic freezer, yet flavoured by chance and change. The dwarf planet royals may dwell in darkness, but their variety shines bright, revealing that even in the outermost reaches of space the universe never stops experimenting. Colour in the Kuiper Belt is a quiet language. Every shade, whether deep red, pale grey or something in between, tells a story about chemistry, sunlight and time. Out there, where the sun is little more than a bright star, colour doesn't come from paint or pigment, but from the way frozen ices and invisible radiation slowly change the very skin of a world. The palette of the Kuiper belt is painted in slow motion, molecule by molecule, across billions of years. Most of these distant objects are made from a familiar collection of ices and rock. Water ice forms the backbone of their structure, giving them solidity beneath their crusts. Mixed in are more delicate substances, frozen methane, nitrogen, carbon monoxide and carbon dioxide. Each behaves differently under sunlight, and together they form a dazzling chemistry lab spread across the solar system's outermost reaches. Where the inner planets rely on warmth and liquid water for transformation, the Kuiper belt does its work in the cold, where even light has to take its time. When sunlight, faint as it is, strikes a Kuiper belt object, it triggers tiny chemical reactions in those frozen surfaces. Radiation from the solar wind, cosmic rays, and ultraviolet light all bombard the ices, breaking apart molecules and recombining them into new, more complex structures. Over immense spans of time, this process produces organic compounds known as tholins, complex tar-like materials that tint the surface a reddish-brown. Tholins aren't unique to the Kuiper belt. They've been created in laboratory experiments here on Earth and are found on Saturn's moon Titan as well. But in the far outer solar system, they form a kind of cosmic varnish, coating the worlds that dwell in the cold. These tholins are responsible for many of the belt's warm ruddy hues. When astronomers observe Kuiper belt objects through telescopes, they see that some are distinctly red, while others appear neutral or grey. That difference hints at a world's history. Redder objects have likely remained in place since the early days of the solar system, their surfaces untouched except by radiation. The greyer ones may have been disturbed, either resurfaced by collisions or warmed enough for fresh ice to bubble up from below, erasing the reddish patina. The slow chemistry that builds these colours is surprisingly delicate. Cosmic radiation constantly darkens and reddens the surface, while impacts or sublimation, when frozen gases vaporize, can strip away the weathered layer, revealing brighter material underneath. It's a cosmic balance between aging and renewal. Some objects have surfaces that look ancient and sunburnt, others appear freshly frosted, as if they've just been repainted by the season. That seasonal paint is more than poetic, it's literal. On some larger Kuiper belt bodies, especially those with thin atmospheres like Pluto or Makemake, sunlight can cause ices to sublimate, turning directly into gas. As the gas drifts across the surface and refreezes elsewhere, it lays down thin layers of frost, altering the reflectivity and sometimes even the colour. Over time, this creates bright patches, dark streaks, and subtle gradients, like an artist blending light and shadow across a frozen canvas. And it all happens very, very slowly. At 40 times Earth's distance from the Sun, sunlight is about 1,600 times weaker. Each photon has made an exhausting journey of nearly 6 hours just to reach its target. You could say that these distant worlds are sun-kissed, but very slowly, and by photons that took all afternoon to get there. The faint sunlight may not provide much warmth, but it does provide energy. Even the weakest rays can drive complex chemistry, especially when combined with the ever-present bombardment of cosmic rays. Those high-energy particles dig deep into the surface, rearranging molecules and building new compounds. Over millions of years, layers of chemistry accumulate, thin, fragile records of each world's long exposure to the deep. The result is a gallery of colour unlike anything closer to home. Some objects, like the cold classicals, glow with rich reddish tones. Others, such as Haumea, appear almost white, their water ice surfaces reflecting most of the light that hits them. Pluto displays both extremes at once, pale nitrogen plains bordered by dark tholin-stained highlands. Eris gleams bright as snow, likely because fresh ice still coats its surface. Even among objects only a few hundred kilometers across, colours vary widely, hinting at subtle differences in temperature, composition and exposure. Each colour tells a piece of a deeper chemical story. The presence of methane, for example, can produce a pinkish tint when exposed to radiation. Nitrogen frost tends to brighten a surface, while carbon-bearing ices once altered produce reddish or brown hues. Water ice alone is nearly colourless, so worlds dominated by it, like Haumea, look pale and reflective. Mix a bit of organic residue into the blend, and you get something darker, richer, more ancient in appearance. But colour isn't only about chemistry, it's also about time. The longer a surface remains undisturbed, the redder and darker it becomes. That's why some of the oldest Kuiper belt objects appear like aged relics, their skins tanned by countless eons of cosmic weather. Younger or more geologically active worlds, by contrast, often look brighter because fresh ice has covered their scars. It's as though the solar system paints and repaints its outer walls, sometimes layering colour so slowly that no human timescale can capture it. Space weathering, as scientists call it, is both an artist and an archivist. It records every burst of sunlight, every particle impact, and every slow thaw. On Earth, weathering breaks down and erodes. In the Kuiper belt, it builds up, darkens, and preserves. With no atmosphere to block radiation and no winds to erase its effects, the evidence of time piles on gently but persistently. For astronomers, decoding these colours is like reading the solar system's diary. By studying how light reflects off different surfaces, they can infer what materials are present and how long they've been exposed. It's not a perfect science. One object's red may come from methane residues, and others from entirely different compounds. But together, they sketch a picture of ongoing evolution in the deep freeze. From a distance, the Kuiper belt looks monochrome, a dim grey ring around the sun. But look closer, and it bursts into a spectrum of soft reds, faint whites, and muted browns, each the product of chemistry, sunlight, and time. In those subtle shades, you can trace the history of billions of years of cosmic art, painted not by brush or hand, but by photons, ice, and silence. So, while the Kuiper belt may seem dark and distant, its beauty lies in the details. The whisper of colour on frozen surfaces, the chemical fingerprints of light that has travelled for billions of kilometres. It is a place where sunlight still matters, where even in the coldest corners of the solar system, a slow, patient glow keeps painting the dark. Out beyond Neptune, between 40 and 50 astronomical units from the Sun, light takes on a different character. It is not gone, but it is tired. The sunlight that reaches the Kuiper belt has travelled for more than 6 hours, stretching and fading as it goes, until it spills across those frozen worlds with only a whisper of its former warmth. What begins at Earth as a bright noonday blaze becomes out here the faintest suggestion of glow, like twilight trapped in perpetual slow motion. At that distance, the sun's power has dwindled to less than 1/10,000th of what it delivers to Earth. The solar flux is so weak that you could stare straight at the sun and see only a small, brilliant star against a black sky. The landscapes illuminated by that pale light are dim and muted, their shadows sharp and unbroken. The temperature of these distant surfaces lingers around -200 degrees Celsius, cold enough to keep nitrogen, methane and carbon monoxide locked as ice. Water ice, which on Earth would melt and flow, here behaves like stone, brittle, solid and eternal. This is what physicists call the effective temperature, a balance between the energy absorbed from sunlight and the energy radiated back into space. In the Kuiper belt, that equilibrium sits just above absolute zero. Each object's temperature depends slightly on its colour, its reflectivity, and its distance from the sun, but even the brightest ones bask in little more than a gentle cosmic chill. If you could touch the surface of one of these worlds, the cold would not feel like a breeze or a frost. It would feel like the absence of motion itself. Time also behaves differently here. A single year for a Kuiper belt object can last 200 or 300 Earth years, or more. The slow orbits stretch time until it feels syrupy and still. Seasons, if they exist at all, can last for decades. A sunrise may take a week to climb above the horizon. On Pluto, for example, one full orbit takes 248 Earth years. Someone born when Pluto last reached its closest point to the Sun would have long since turned to dust before it returned again. Imagine what that means for weather, for light, for the rhythm of day and night. Half a world might remain in darkness for centuries before the sun returns to kiss it with a faint glow. During that time, temperatures plunge even further, and gases that once formed a thin atmosphere freeze and settle back onto the surface as frost. Then, centuries later, the sun returns, and that frost begins to sublime again, vaporizing back into gas, drifting across the landscape and refreezing elsewhere. Entire atmospheres inhale and exhale with the slow pulse of orbital time. Geology, too, follows a pace that would test any patience but the universe's own. Craters, once carved, linger for billions of years, softened only by the faintest creep of ices that flow slower than any glacier on Earth. Where sunlight touches an icy slope, it can cause subtle changes, tiny movements of sublimation or sintering, but such processes unfold on timescales that make human history seem like a flicker. The crusts of these worlds grow hard and ancient, their layers preserving the faint memory of every solar breeze, every cosmic ray, every rare impact. Because sunlight is so weak, heat does not travel far. A few centimeters below the surface, the temperature barely changes from one millennium to the next. Scientists call this property thermal inertia, the tendency of material to resist temperature change. The dense crust of a Kuiper belt object holds its cold like a secret, insulating the deeper layers from the brief influence of sunlight. If you were to dig beneath the surface, you would find ancient ices that have not melted or shifted since the solar system's birth. Even shadows here are not ordinary. On Earth, a shadow cools, but eventually the air around it warms again. In the Kuiper belt, a shadow can trap ices for eternity. A rock or a crater rim might block sunlight for thousands of years, preserving frozen nitrogen or methane that would have otherwise evaporated into space. When sunlight finally returns, centuries later, the ice may briefly shimmer and sublimate, only to freeze again as the long night resumes. The rhythm is glacial, deliberate, and oddly peaceful. Because temperatures are so low, chemical reactions crawl almost to a stop. Molecules that would break apart in seconds on Earth can remain intact for millions of years. The Kuiper belt, in this way, is a cosmic refrigerator, a place where time's chemistry slows enough to preserve the ingredients of the early solar system. Astronomers studying these ices are essentially peering into a deep freezer that has kept its contents unchanged for over 4 billion years. It's a strange irony. The farther from the sun you go, the more enduring things become. Heat creates activity, erosion, and renewal, but cold preserves. Mountains don't crumble, rivers don't flow, and winds never stir the dust. The Kuiper belt's landscapes are suspended between creation and decay, frozen in a kind of geological meditation. Even when changes happen, they happen so gently that they feel more like breathing than motion. If you were to stand on one of these distant worlds and look up, time would seem almost still. The sun, small and steady, would cast light so faint you might see stars even at midday. Days and nights would stretch unimaginably long, their transitions soft and slow. You might feel, if you could feel at all in the cold, that the universe itself had slowed its heartbeat. Out here, clocks tick softly where sunlight is a rumour. Centuries pass in the space of a sigh. The pace of time is measured not in hours or days, but in the quiet movement of light across a frozen plain, in the long journey of a photon leaving the sun, and finally arriving at a grain of ice 40 times farther than Earth. The Kuiper belt reminds us that time isn't the same everywhere. In the warmth of the inner solar system, change is quick and constant. Volcanoes erupt, rivers cut valleys, and winds sculpt dunes. But in the deep cold beyond Neptune, time itself becomes brittle. Things endure. The same sunlight that drives life on Earth becomes here a faint pulse, barely enough to stir the surface, yet still enough to whisper across the dark. So when you picture the Kuiper belt, imagine a world where the light never rushes, where centuries drift by like lazy snowflakes, and where even shadows can last 1,000 years. It is the solar system's quietest place, where time moves so gently that it almost feels asleep. In the calm outskirts of the solar system, companionship is surprisingly common. Many of the Kuiper belt's icy bodies are not alone at all, but exist in pairs, two objects orbiting each other in a slow, frozen waltz. Among the cold, classical Kuiper belt population, nearly half of all known objects are binaries. That's an astonishing number when compared to the inner solar system, where binary asteroids are rare and short-lived. The Kuiper belt, it seems, is a place where gentle beginnings still show, and delicate partnerships can endure for billions of years. These binaries tell us something profound about how the outer solar system formed. They suggest that collisions here were not the violent, high-speed impacts that shaped the rocky planets closer to the sun, but slow, graceful encounters, more like drifting icebergs brushing together than meteors colliding. In the deep freeze of the Kuiper belt, where orbital speeds are low and gravity's pull is weak, two small bodies could meet, circle one another, and settle into a mutual orbit without tearing each other apart. Their bond is gravity's soft handshake, not its clenched fist. Astronomers studying these pairs have found that many of them are nearly equal in size. Some orbit each other at such a distance that they're like cosmic dance partners, connected by an invisible string, looping through space together. Others are so close that they may, over time, have touched and fused, creating what we call contact binaries. These are the ultimate expression of the Kuiper belt's calm environment. Two bodies that drifted together so slowly that instead of shattering they simply joined. The most famous example of this is Arakoth, the small snowman-shaped world visited by NASA's New Horizons spacecraft on New Year's Day of 2019. When the images first came back, scientists were astonished. Arakoth looked nothing like an asteroid or a comet. It was made of two connected lobes, one larger, one smaller, joined by a narrow neck. The surface was smooth and lightly cratered, a soft blend rather than a scarred scarline. This was no catastrophic collision, it was a cosmic embrace that happened at walking speed. Arakoth's very existence tells a story of gentleness. Its two lobes likely formed from the same local cloud of material, orbiting each other closely as they accreted. Over time, drag from surrounding gas and tiny particles slowed their orbits until they finally merged. If the meeting had been even slightly faster, both bodies would have shattered into fragments. Instead, they became one. Two snowballs that leaned in and never left. The neck connecting the two lobes is particularly intriguing. It appears brighter and smoother than the rest of the surface, suggesting that fine particles may have trickled down and settled there after the merger. It's the scar of union, but a peaceful one, more like a gentle seam than a wound. From end to end, Arakoth measures about 35 kilometers, and its shape captures the essence of how objects once grew in the early solar system, not through violent collisions, but through careful, quiet assembly. The colours of Arakoth add another clue. Its surface shows a warm reddish tone, the mark of tholins and other radiation-processed organics. That chemistry, combined with its unbroken form, indicates that it has remained largely untouched since the dawn of the solar system. It is a time capsule from the age of planet building, a relic of an era before chaos took hold. The Kuiper belt, with its vast distances and slow rhythms, preserved it like a fossil in cosmic amber. Arakoth isn't alone in its strangeness. Other Kuiper belt objects show evidence of binary histories too, some still orbiting in pairs, others perhaps merged long ago. These systems help scientists understand how gravity and motion behave in the cold outer regions. When two small bodies come close enough, their mutual pull can dominate over the sun's faint tug, allowing them to orbit each other indefinitely. If that pair experiences no major disturbance, no passing giant planet, no disruptive collision, they can survive together for billions of years. That stability explains why so many binaries remain intact. The Kuiper belt is sparse, and encounters between objects are incredibly rare. Once two bodies find each other, nothing much comes along to interfere. They can drift together through the ages, orbiting so slowly that their entire dance might take weeks, months, or even years to complete. Their bond becomes one of the most enduring in the solar system, frozen both in time and in temperature. Some binaries may eventually spiral inward, their orbits shrinking due to tidal interactions or the faint drag of outgassing ices. When that happens, they might merge into contact binaries like Arakoth. Others will remain at a comfortable distance forever, orbiting in quiet companionship until the sun itself fades. For planetary scientists, these systems are more than curiosities. They're living evidence of how planets once began. The process that formed binaries in the Kuiper belt may be similar to how the seeds of larger worlds first assembled. In those early days, small clumps of material would have coalesced, orbited one another, and merged gently, layer by layer. Arakoth simply froze in time before that process could continue, showing us what the earlier steps of planet building looked like before the heat and chaos of gravity took over. The fact that such delicate objects still exist is nothing short of miraculous. Closer to the sun, gravitational interactions, impacts and heating would have destroyed them long ago. But in the deep quiet of the Kuiper belt, there's no rush, no violence, no storms of radiation strong enough to erase them. The same stillness that slows time here also preserves form. When you imagine these paired worlds, think of them not as cold rocks, but as participants in a gentle ballet. Each motion is graceful, each orbit perfectly tuned to the other's rhythm. Some circle tightly, others at vast distances, but all share the same quiet partnership that has lasted since the dawn of the solar system. It's the universe's most patient waltz, set to a tempo that only eternity could keep. And so the Kuiper belt, far from being a graveyard of frozen debris, becomes a gallery of ancient relationships. In its vast emptiness, companionship endures, not through force, but through balance. Two snowballs leaning together across the cold, finding peace in the silence. In a solar system that began in chaos and collision, these delicate pairs remind us that creation too can be gentle. In the Kuiper belt, even collisions happen in slow motion. The space between objects is so vast and their orbital speed so gentle that when two bodies finally meet, the impact is often more of a nudge than a smash. Compared to the fiery violence of the inner solar system, where asteroids strike at tens of kilometers per second, the encounters out here are quiet, glacial, almost polite. Yet over billions of years, these slow-motion impacts have subtly sculpted the surfaces of distant worlds, leaving behind craters, scars, and patterns that whisper stories of time, not turmoil. Craters are the Kuiper Belt's version of fossils. They record the history of impact stretching back to the solar system's earliest days. Each depression, each ring of ejected ice, marks a moment when two ancient travellers briefly touched before parting ways forever. But because the impacts are slow, the results look different from those on rocky planets. The walls of Kuiper Belt craters are often shallower, their rims softer, their floors smoother. Instead of splintering into shards, the icy crust absorbs much of the impact, compressing rather than exploding. On Pluto, for instance, the New Horizons spacecraft revealed craters that seem unusually subdued. Some have been softened or erased entirely, not by wind or water, but by the slow movement of ices over geological timescales. Methane and nitrogen ice can creep like putty under their own weight when given enough time. Even at temperatures hundreds of degrees below freezing, they can slowly flow and fill in craters, like dough settling into a pan. In such places, the surface renews itself not through eruptions or erosion, but through the quiet rearrangement of molecules over millennia. The composition of these distant surfaces plays a key role in how craters form and endure. Many Kuiper Belt objects are made of a mixture of rock, dust, and ices, with high porosity, meaning they're not dense and solid, but rather fluffy, filled with tiny voids. Imagine a cosmic snowball lightly packed rather than frozen hard. When a smaller body collides with such a target, it doesn't create a sharp, glassy crater like one on the moon. Instead, the energy of impact is absorbed and dispersed through the porous layers, producing rounded depressions with muted edges. Over time, additional impacts may sprinkle fine particles, regolith, across the surface, forming a powdery blanket of debris that further smooths the landscape. This regolith acts as insulation, shielding the layers beneath from temperature fluctuations and cosmic radiation. It's like a protective quilt spread over ancient terrain. Even a thin layer of this loose material can preserve delicate features for billions of years, and because new impacts are so rare, many of these surfaces remain remarkably well preserved. The Kuiper Belt, unlike the turbulent inner solar system, is a place where the past stays put. Yet even in this quiet, collisions still matter. Occasionally two larger bodies do meet with enough energy to shatter. When that happens, fragments scatter through space, forming what astronomers call collisional families, clusters of smaller objects sharing similar orbits and composition. Haumea, one of the Kuiper Belt's dwarf planet royals, is thought to be the center of such a family. Its rapid spin and elongated shape suggest a massive impact long ago, one that spun it up and sent shards of icy debris drifting outward. Those fragments now orbit the Sun as individual objects, still bearing the chemical fingerprint of their shared origin. These families tell us that even in the outer solar system, destruction and creation are intertwined. Every impact reshapes, redistributes, and sometimes even births new worlds. But because the collisions are slower and the materials more fragile, the outcomes are subtler. Rather than obliterating, they carve softly. Rather than melting rock, they rearrange ice. The result is a kind of gentle sculpting that gives the Kuiper Belt its texture, a landscape shaped not by storms but by whispers. Scientists can estimate the ages of Kuiper Belt surfaces by counting craters, just as they do on the Moon or Mars. But here, the logic bends a little. A surface with few craters might mean it's young, or simply that the environment is so quiet that few impacts have occurred. A world blanketed in ancient ices might appear pristine, not because it's new, but because it has lain undisturbed since the solar system's infancy. The absence of scars in this case is its own kind of history. Craters also reveal layering, subtle differences in how deep or dark the material becomes beneath the surface. When an impact digs into a Kuiper belt object, it exposes the internal composition, allowing astronomers to glimpse what lies below. Some craters appear brighter than their surroundings, suggesting fresh, unweathered ice beneath. Others look darker, perhaps revealing deposits rich in complex organics or radiation-altered material. Each crater, in its quiet way, opens a small window into time. Over billions of years, the balance between impact and rest has created a unique kind of landscape. It's neither chaotic nor static, but somewhere in between. A frozen rhythm of change that moves too slowly for human senses to grasp. The Kuiper belt doesn't roar or crumble, it exhales softly. Its surfaces evolve through impacts that happen once in 1,000 lifetimes, through frost that creeps grain by grain, through heat that seeps millimeters into the crust before fading back into space. Even the largest impacts here are muted. A collision that would vaporize rock on Earth or melt iron on Mercury may, in the Kuiper belt, simply compress and deform. The cold turns shock into silence. The craters it leaves behind are the fingerprints of patience, evidence of a cosmos that knows no hurry. From afar, it's tempting to think of these distant objects as static, frozen relics. But look closely, and you see the slow artistry of physics at work. A shallow crater darkens over centuries as tholins form on its floor. A rim softens as methane frost creeps across it. Tiny grains of dust settle in the silence, filling gaps that no wind will ever touch. Nothing happens quickly, but everything happens eventually. It's a reminder that even in the stillest corners of the universe, time is never truly idle. The Kuiper belt's craters are not wounds, they're brushstrokes, records of gentle collisions that shape the outer solar system grain by grain. And though the process may be quiet, its result is breathtaking, a landscape that endures through peace, moulded not by violence, but by the long patience of cold and time. The Kuiper belt doesn't end where it sits. It breathes slowly and invisibly, sending some of its frozen children inward toward the sun. Every so often, gravity reaches into that distant realm and plucks an icy body from its orbit, nudging it onto a new path. What begins as a quiet drift at the edge of the solar system can, over millions of years, turn into a fiery display near the inner planets. These travellers are comets, the wandering storytellers of the cosmos, and their long journeys begin in the cold cradle of the Kuiper belt. Most of the time, the objects in the Kuiper belt are content to remain where they are, circling the sun in peace. But even in that vast stability, small gravitational influences build up over time. A passing star, the faint tug of Neptune, or a distant resonance can slowly alter an orbit. These changes are tiny from year to year, but over eons they add up, like the patient tick of an unseen clock. Eventually, one of these icy bodies may find itself nudged onto a new trajectory, one that carries it closer to the sun. When this happens, the object's quiet, frozen existence begins to change. It leaves the calm of the Kuiper belt and enters a more turbulent realm, where the giant planets roam. These intermediate travellers are known as centaurs, a fitting name since they bridge two worlds. Part Kuiper belt object, part comet in waiting. The centaur's orbits cross those of Jupiter, Saturn, Uranus, or Neptune, and their lives are short by cosmic standards, only a few million years before they're ejected, captured, or transformed. Centaurs are some of the most unpredictable wanderers in the solar system. Their paths twist under the influence of the giant planets, and their surfaces begin to show the first hints of change. Some remain dormant, their ice is still locked beneath crusts of darkened material. Others begin to show faint activity, tiny jets of gas or dust as the sun's warmth stirs their frozen chemistry. Astronomers have even caught a few centaurs in the act, sporting short-lived comas or tails, like half-formed comets caught between two states of being. Eventually, gravity and chance may send one of these centaurs deeper into the inner solar system. When it comes under the influence of Jupiter, its orbit often shortens dramatically, turning it into what astronomers call a Jupiter family comet. These comets typically take less than 20 years to complete an orbit and return again and again to the Sun's neighbourhood, gradually losing their icy reserves with each pass. It's at this stage that a once frozen body from the Kuiper belt finally awakens. As it nears the Sun, sunlight begins to warm its surface. Ices that have remained solid for billions of years, water, carbon dioxide and methane, start to sublimate directly into gas. The escaping vapours carry tiny dust grains with them, forming a glowing coma around the nucleus. Solar radiation and the solar wind then push these materials outward, creating the distinctive tail that points away from the Sun. The comet, now fully alive, becomes a transient spectacle visible even from Earth, a snowy messenger thawing by a distant fire. Each time it loops around the Sun, a comet loses a little more of its mass. Over thousands of years, this erosion eats away at the nucleus, leaving behind a trail of dust and fragments that can eventually form meteor showers on Earth. The process is both destructive and revealing. As comets shed their layers, they expose the untouched materials that lie beneath, the chemical fingerprints of the solar system's earliest days. That's what makes these travellers so scientifically valuable. Comets are time capsules preserving the chemistry of the protoplanetary disk from which the planets were born. They contain water, simple organic compounds, and even the building blocks of more complex molecules. By studying them, astronomers can learn not only about how the solar system formed, but also about how life's ingredients may have spread across space. Some of the most revealing discoveries have come from missions that dared to meet comets up close. The Rosetta spacecraft, which orbited Comet 67 P/Churyumov-Gerasimenko, found organic molecules including amino acid precursors on its surface. Earlier missions to comets like Halley and Wild too uncovered a mix of minerals and carbon compounds that pointed to a surprising truth. Material from the inner and outer solar system had already mingled even before the planets were fully formed. In that sense, comets are not just messengers from afar. They're reminders that everything in our cosmic neighbourhood is connected. And then there's the question of water. Earth's oceans may owe part of their existence to comets. Some scientists believe that impacts from icy bodies early in Earth's history delivered significant amounts of water and volatile materials, helping to shape our planet's habitability. Not all comets match Earth's exact water composition. Many contain slightly different isotopic ratios, but others, particularly those linked to the Kuiper belt, come surprisingly close. It's possible that the water you drink, the ice in your freezer, or the rain that falls on your skin all trace their lineage to ancient collisions with visitors from beyond Neptune. But for every comet that becomes a celestial spectacle, countless others remain unseen, orbiting quietly in the shadows. The Kuiper belt holds an enormous reservoir of these potential travellers, millions, perhaps billions, of icy bodies waiting for a gravitational whisper to set them on their way. It is, in a sense, a great cosmic pipeline, slow-moving at one end, lively at the other. From the frozen calm of the belt to the fiery proximity of the Sun, comets follow an elegant trajectory that spans both silence and spectacle. Their journeys also mark the solar system's natural recycling process. Material that once lay dormant at the edge can be drawn inward, transformed by heat, and eventually return to space as dust and vapour. The Kuiper belt supplies, the sun sculpts and gravity redistributes, a slow, endless cycle that keeps the solar system in quiet motion. To imagine a comet's life is to imagine extremes of temperature, time and change. For most of its existence it sleeps in the dark, untouched by warmth or motion. Then, suddenly, after billions of years, it is awakened. Its ice is hissing, its tail stretching millions of kilometers into sunlight. And just as suddenly, it retreats again, fading back into the dark, its story half told until the next return. Every time we see a comet streak across the night sky, we're witnessing that story unfold, a tale that began long before Earth's first oceans formed, and that will continue long after they're gone. These snowy messengers thawing by a distant fire are proof that even the coldest places in the universe still have stories to tell. They are the whispers of the Kuiper belt carried inward on trails of light, reminding us that the past is never lost. It simply drifts, waiting for the right warmth to awaken it again. Finding a Kuiper belt object is a little like trying to spot a snowflake drifting across a city skyline, while standing hundreds of kilometers away. These worlds are unimaginably faint, astonishingly slow, and hidden among millions of brighter stars. Yet somehow, astronomers have managed to find thousands of them, one by one, through a mixture of patience, clever technique, and quiet persistence. It's a story not of grand discoveries made overnight, but of tiny movements noticed after years of watching the dark. The first challenge is simple to describe and almost impossible to overcome: distance. The Kuiper belt begins around 40 times farther from the Sun than Earth. At that range, sunlight is so weak that it barely reaches the surfaces of these objects, and even when it does, very little is reflected back. Most Kuiper belt objects are smaller than our Moon, and darker than coal. Even with the most powerful telescopes, they appear as single, dim points of light, indistinguishable from the countless background stars scattered across the sky. To find one, astronomers rely on motion. Stars, of course, don't move perceptibly from night to night. But Kuiper belt objects, orbiting the Sun, shift ever so slightly against that fixed background. The motion is agonizingly slow, sometimes just a few arcseconds per hour, a fraction of the width of a human hair held at arm's length. Detecting it requires careful observation over many hours, sometimes even years. This is where time-lapse tracking comes in. Astronomers take multiple images of the same patch of sky, often hours or days apart, and then compare them. Most points of light stay perfectly still, but every now and then one faint dot moves, a tiny wanderer making its way through the heavens. Early astronomers used photographic plates and painstakingly compared them by eye, sliding them under microscopes to look for anything that had shifted. Today, computers perform much of that work, blinking images rapidly to highlight any speck that has changed position. It's a bit like watching a stop-motion film of the night sky, where the stars stand frozen and only the shyest characters creep across the frame. Once a moving object is spotted, the next step is confirmation. A single observation might catch a satellite flare, a cosmic ray, or a digital artifact. To know it's real, astronomers must track it again and again and again. Weeks later, with enough data points, the object's orbit can be estimated. Months or even years later, that orbit becomes precise enough to prove the new discovery is indeed a Kuiper belt resident. Finding one of these worlds is not a moment of sudden revelation. It's a slow bloom of certainty, unfolding as the data deepens. Modern sky surveys have revolutionized this process. Rather than staring at one region of the sky, large survey programs scan vast stretches systematically, capturing thousands of images each night. Sophisticated algorithms then sift through the data, comparing frames and flagging any object that moves just a little. The technology has advanced, but the spirit of discovery remains the same. patient, methodical, and driven by curiosity rather than speed. Even with powerful instruments, though, direct imaging can only go so far. Many Kuiper belt objects are simply too faint to see directly, even with the largest telescopes. For these invisible worlds, astronomers use a different and rather elegant technique: stellar occultation. The concept is simple, but breathtaking in its precision. When a Kuiper belt object passes in front of a distant star, it momentarily blocks some of the starlight. To an observer on Earth, the star appears to flicker or briefly disappear, a tiny blink against the dark. By timing this blink with extraordinary accuracy, astronomers can learn a surprising amount. The duration of the occultation reveals the object's size, while subtle dips or fluctuations in brightness can indicate whether it has an atmosphere or even rings. It's like shining a flashlight through a keyhole and deducing the shape of the room beyond from the shadows that dance across the wall. This technique has led to some of the most delicate discoveries in planetary science. Rings around Quaoar and Haumea were first hinted at through occultations, their signatures appearing as faint symmetrical dips in starlight before and after the main event. Pluto's tenuous atmosphere was detected in much the same way decades before any spacecraft reached it. Each observation requires near-perfect timing, often involving coordinated efforts from telescopes around the world. If even one cloud drifts in front of the star at the wrong moment, the opportunity is lost, and there might not be another for years. Patience, then, is not just a virtue in Kuiper belt astronomy, it's a necessity. These worlds move slowly, their alignments rare, and their signals faint. Discoveries are measured not in nights of observation but in seasons, sometimes decades. Astronomers might wait years for a predicted occultation, rehearsing every calculation, every adjustment of instruments, just to capture a dip in light that lasts a few seconds. When it works, though, those few seconds can rewrite what we know about a distant world. Even when a Kuiper belt object has been found, the work continues. Tracking its motion over time refines our understanding of its orbit and can reveal whether it belongs to a specific family or resonance. Its brightness can vary subtly as it rotates, hinting at shape, texture, or perhaps a companion. Every detail adds to a growing picture of the outer solar system, a mosaic built one faint pixel at a time, and sometimes the discoveries come not from what's seen, but from what's missing. A predicted object that fails to appear during an occultation can reveal a hidden atmosphere refracting light around it. A star that dims too long might suggest that the object has a moon. Even small irregularities can open vast doors of interpretation. In truth, the study of the Kuiper belt is an act of faith in faintness. Astronomers chase shadows, blink comparisons and subtle dips in starlight, trusting that these traces add up to real worlds. The scale of patience required is extraordinary. Imagine searching for something smaller than a city, farther than Neptune, moving slower than a drifting cloud, and doing so across a sky filled with hundreds of millions of stars. Yet it works. From these whispers of data, entire populations of icy worlds have been revealed. What was once thought to be empty space beyond Neptune is now known to be rich with complexity. Dwarf planets, binaries, contact pairs, and countless smaller bodies. Each discovery began as a faint dot, barely noticed at first, that slowly transformed into a member of the solar system's frozen frontier. There's something quietly poetic about this kind of astronomy. It isn't about fireworks or instant revelations. It's about the long, slow gaze into darkness, the willingness to let time do the talking. In a way, it mirrors the Kuiper belt itself, calm, enduring, and patient beyond measure. The astronomers who study it have learned to listen at that same tempo, to notice movement where most would see stillness, and to celebrate the invisible as much as the seen. The Kuiper belt doesn't announce its presence with brilliance or sound. It reveals itself through motion, through light that blinks, through the smallest possible changes that only the most attentive eyes can see. To find its worlds is to learn the art of stillness, of watching long enough for the faintest spark of motion to whisper, "I'm here." In July of 2015, after a journey of nearly 5 billion kilometers and 9.5 years, a small spacecraft about the size of a baby grand piano swept silently past Pluto. For decades, that distant world had been nothing more than a smudge in telescopes, a tiny blurry point of light orbiting on the edge of everything. Then, in the span of a single summer day, it became real. The New Horizons flyby turned a pixelated dot into a living landscape, and what it revealed was far more dynamic, strange, and beautiful than anyone had dared to expect. As New Horizons approached, Pluto's faint glow began to sharpen. The spacecraft's cameras, designed to capture every possible detail during its one and only pass, sent back images that astonished scientists. Instead of a uniform frozen sphere, Pluto's surface was a patchwork of colours and textures, rugged mountains, smooth plains, dark streaks, and bright patches, each telling a different story of ice and time. The most iconic feature soon emerged, a vast heart-shaped expanse known as Tombor Regio, named for Pluto's discoverer, Clyde Tombaugh. Within that heart lies Sputnik Planitia, one of the most remarkable terrains in the solar system. It's a vast icy basin, filled not with water ice, but with nitrogen ice that flows and convects like glaciers on Earth. In Pluto's feeble sunlight and bitter cold, around minus 230 degrees Celsius, these ices can still move, slowly creeping across the surface, carrying blocks of frozen water that float within them like icebergs in a frozen sea. The plane surface is patterned with polygonal cells, shaped by convection currents that rise and fall beneath the crust, as if Pluto's heart was still faintly beating beneath its frozen skin. What startled scientists most was how young parts of Pluto's surface appeared. Sputnik Planitia showed almost no impact craters, meaning it must have been resurfaced relatively recently, perhaps within the last few tens of millions of years. That's practically yesterday in planetary time. Some regions, by contrast, are ancient, pocked and scarred by billions of years of collisions. Others seem to fall in between, showing hints of erosion, collapse, or glacial creep. This diversity suggests that Pluto is not geologically dead, but quietly active even now. Mountains rise several kilometers high at the edges of Sputnik Planitia, composed of solid water ice that's as hard as rock under such low temperatures. These peaks, some towering more than 4 kilometers, cast long shadows across the plains. Elsewhere, strange ridges and hummocks hint at uplift and freezing processes that no one yet fully understands. It's as if Pluto is sculpting itself slowly, patiently, with the limited energy it still has left. One of the most tantalizing questions raised by New Horizons was whether Pluto might still harbour a subsurface ocean. Some models suggest that the impact basin of Sputnik Planitia could have formed in a way consistent with liquid water beneath the crust, a hidden ocean insulated by layers of ice and antifreeze-like compounds such as ammonia. The evidence remains subtle and uncertain, but intriguing, a hint that even in this distant frozen realm, warmth and motion might persist below the surface, quietly defying the cold. Above all this icy terrain lies a delicate layered atmosphere, faint but complex. As New Horizons looked back at Pluto with the sun shining through its thin veil, it captured something unexpected, an ethereal blue haze encircling the world. The haze created by sunlight interacting with methane and other gases builds fine particles that scatter blue light, a stunning echo of Earth's own sky, though formed under completely alien conditions. That hazy halo was one of the mission's most emotional images, a glowing rim of light around a world that had, until then, seemed too distant to ever shine. But Pluto's story is not told alone. Its largest moon, Charon, is almost half its size, making the two more of a binary system than a planet and a satellite. New Horizons flyby revealed Charon as a world of its own, marked by immense canyons, rugged plains, and a striking dark patch near its north pole nicknamed Mordor Macula. The canyon system, stretching more than 1,000 kilometers, suggests Charon's crust once cracked as internal water froze and expanded. It's as though the moon's skin split open, leaving behind cliffs and chasms that dwarf the Grand Canyon many times over. The dark polar stain on Charon's surface adds a touch of mystery. Scientists think it may be formed from gases escaping Pluto's atmosphere, which drift across space and then freeze onto Charon's pole, where they undergo slow chemical reactions driven by ultraviolet sunlight. Over time, this cosmic spray painting leaves behind a reddish-black residue of tholins, the same complex organic compounds that tint many Kuiper belt worlds. In this way, Pluto and Charon share not just gravity, but chemistry, each influencing the other in a delicate cosmic exchange. New Horizons also captured Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra. Tiny and irregularly shaped, they whirl around the central pair in orbits that are surprisingly chaotic. Because Pluto and Charon orbit a common centre of gravity rather than one dominating the other, these smaller moons are constantly being tugged in multiple directions, like dancers trying to follow 2 partners at once. Their spins are erratic, tumbling unpredictably as they travel, yet they've remained in stable orbits for billions of years. The New Horizons mission didn't linger. It swept through the Pluto system in just a few hours, then continued its journey deeper into the Kuiper belt. But in that brief encounter, it transformed our understanding of what small worlds can be. Before the flyby, Pluto was expected to be an inert ball of frozen nitrogen, a relic of formation. Instead, it revealed itself as a complex, active and evolving world, a frontier where ice behaves like rock and geology still stirs in the dark. Even the images themselves carried a quiet weight. For decades, Pluto had existed only as a few blurry pixels, a symbol of the solar system's unreachable edge. Seeing it up close for the first time was like meeting a myth made real. There it was, a heart-shaped plain, a haze glowing blue, mountains catching the faint sunlight. What had once been distant and abstract suddenly felt familiar and alive. It was as if the universe had pulled back a curtain and whispered, "There's still wonder waiting out here," and perhaps that was New Horizons' greatest achievement. Beyond the data and the discoveries, it reminded humanity that even the smallest, coldest worlds can surprise us. That beauty is not confined to warmth or light, but can bloom in the shadowed reaches of the solar system. Pluto, once the forgotten planet, became a symbol of curiosity fulfilled, a reminder that the farther we look, the more alive the cosmos becomes. As the spacecraft continued onward into the Kuiper belt, it left Pluto shrinking behind it, a blue-hazed jewel fading into starlight. But it also left something here on Earth, the realization that even at the edge of the sun's light, there are landscapes that move, breathe, and shimmer. A world once seen as a mere dot had become a place with glaciers, mountains, and skies, a tiny heart beating softly in the dark. Drifting more than 6.5 billion kilometers from the sun, beyond even Pluto's faint orbit, a small peanut-shaped world called Arakoth floats in near-perfect silence. Its name, drawn from the Powhatan language, means sky, and it feels fitting, because this tiny body seems to hold a piece of the sky's earliest memory. When the New Horizons spacecraft flew past Arakoth on New Year's Day of 2019, it revealed not just another icy rock, but something profoundly older. A cosmic time capsule, almost unchanged since the solar system began. At first glance, Arakoth looks simple, two rounded lobes joined by a narrow neck, like a pair of snowballs that lean together and never drifted apart. But beneath that simplicity lies a wealth of information. Its shape alone tells a story billions of years in the making. The larger lobe and the smaller one appear to have gently merged at walking speed, perhaps just a few meters per second, far slower than a car in a parking lot. This was no cataclysmic collision. It was a soft union, the quiet handshake of two drifting worlds that shared the same orbit around the newborn sun. That gentle contact makes Arakoth a living clue to how planets began. In the early solar system, dust and ice particles clumped together inside the protoplanetary disk, forming larger and larger aggregates, pebbles, then boulders, then kilometre-scale bodies. But scientists have long puzzled over how those early clumps managed to stick without shattering. Arakoth offers an answer. It shows that accretion could happen in calm local environments where collisions were slow enough to allow sticking rather than breaking. In other words, Arakoth is what happens when gravity whispers instead of shouts. The surface of Arakoth is surprisingly smooth, with only a few small craters. Its terrains are gently undulating, not jagged or shattered. The connection between its two lobes shows little sign of violent deformation, suggesting the merger was so soft that the materials barely compressed. There's even a hint of a shallow groove circling the smaller lobe, possibly the remnant of its slow spiral inward before joining the larger one, as if the two bodies danced for a while before settling into embrace. In colour, Arakoth carries the subdued reddish tone characteristic of many Kuiper belt objects. This hue comes from tholins, complex organic molecules formed when ultraviolet sunlight and cosmic rays interact with simple ices like methane, nitrogen, and carbon monoxide. Over billions of years, this slow cosmic tanning deepened the colour of its surface, painting it with a reddish-orange tint. Yet, unlike more heavily processed worlds, Arakoth's coloration shows subtle gradients between its lobes. These variations suggest that before merging, the two halves may have formed in slightly different parts of the same nebular region, close neighbours but not identical twins. This small difference adds depth to its story. It means Arakoth preserves not just the record of a gentle collision, but also the local diversity of the solar nebula, the tiny chemical and thermal variations that once rippled through the disk. By studying how light reflects from its surface, scientists can infer the composition of its ices and organics. The reflectant spectrum hints at a mix of methanol and other frozen compounds, lightly processed by radiation, but still remarkably pristine. In other words, Arakoth has barely changed since it formed. It is as close to primordial as anything we've ever seen. That preservation is what makes it so valuable. Most other bodies in the solar system, planets, moons, even asteroids, have been transformed by heat, pressure, or impacts. Arakoth, in contrast, has remained in the deep freeze since the solar system's first days. It's a survivor from a time before planets existed, before orbits stabilized, before the sun's light fully cleared the surrounding dust. To study it is to look back at the solar system's rough draft, a page written in the language of ice and gravity before the final edits of time. The smoothness of Arakoth's surface suggests it hasn't suffered much bombardment since it formed. That's partly because it lives in the Kuiper belt's quiet zone, where collisions are rare and relative speeds are low. Its preservation is so complete that even the smallest surface variations tell scientists about its internal structure and formation history. By comparing its craters to those on Pluto and Charon, researchers estimate that Arrokoth's surface dates back more than 4 billion years, essentially unchanged since the solar system's infancy. In many ways, Arrokoth bridges the gap between dust grains and planets. It's large enough to have accumulated its own shape and structure, yet small enough to retain the simplicity of its origins. The lack of layering, fractures, or evidence of internal melting indicates that it never warmed enough for differentiation, the process by which heavier materials sink inward and lighter ones rise. Everything inside Arrokoth is still mixed, just as it was when it first came together. It is quite literally a frozen memory. The chemistry on its surface supports this idea of near-total preservation. Unlike Pluto or other larger Kuiper belt objects, Arrokoth doesn't have enough gravity to hold on to an atmosphere or experience significant resurfacing. Its materials are exposed directly to space, altered only by slow radiation chemistry. Spectroscopic analysis reveals methanol ice and complex organics, but little evidence of volatile loss or fresh deposits. It's as though the ingredients that once swirled in the protoplanetary disk simply stopped moving, settled, and stayed put for billions of years. From a scientific perspective, Arrokoth confirmed that the early solar system wasn't a violent demolition derby of colliding rocks, as once imagined. Instead, it appears that at least some regions, especially the cold, distant ones, were serene enough for slow growth and delicate assembly. The process, sometimes called pebble accretion, involves small particles drifting inward through the disk and gradually sticking together under mutual attraction. Over time, these clusters grow, merge, and compact, forming the first building blocks of planets. Arrokoth shows that this process can produce stable, complex bodies without destructive impacts. But beyond the science, there's something quietly poetic about it. After all, Arrokoth has been orbiting the Sun for over 4.5 billion years, never melting, never breaking, just keeping its slow, steady path. When New Horizons arrived, it found not a relic of violence, but a portrait of stillness, a world shaped by gentleness, preserved by cold, and revealed by curiosity. The images of Arrokoth, when first released, carried a strange sense of familiarity. It looked simple enough that you could almost imagine holding it in your hand, its lobes fitting softly against your palm like an ancient river stone. Yet that shape, those two merged worlds, represents an entire epoch of cosmic history. It is evidence that planets began as quiet unions, not catastrophic collisions, that the story of our solar system started not with explosions, but with embraces. In Arrokoth, we see the solar system's childhood preserved, the calm before the chaos, the softness before the storms of planetary growth. Every smooth curve and gentle ridge is a reminder that even at the dawn of creation, the universe already knew how to take its time. It didn't rush to build worlds, it let them drift together, slowly, until gravity's patience turned dust into destiny. And so, floating out there in the farthest shadows of sunlight, Arrokoth remains, unchanged, unhurried, quietly keeping the memory of the beginning. A time capsule from the age when everything was still becoming. A frozen whisper from the first heartbeat of the solar system. Out in the Kuiper belt, the concept of an atmosphere becomes something almost philosophical. It's not the thick, billowing air that swirls above planets like Earth or Venus. Here, it's more like a sigh, thin, fragile and fleeting. A whisper of gas clinging to frozen surfaces, shifting with the faintest changes in sunlight. Some of the largest Kuiper belt objects like Pluto, Eris, and possibly Makemake. briefly possess these ephemeral veils of vapour, forming and vanishing over the course of centuries or even decades. To call them atmospheres feels generous. They're more like exhalations from a deep cosmic sleep. On Pluto, for instance, the presence of a wispy atmosphere was confirmed long before any spacecraft arrived. When it moves closer to the Sun during its long elliptical orbit, just a little extra warmth causes surface ices, mainly nitrogen, with traces of methane and carbon monoxide, to sublimate into gas. This vapour spreads around the world, forming a delicate shell that glows faintly blue in scattered sunlight. It's incredibly thin. The surface pressure is only a few microbars, 100,000 times less than Earth's. Yet for Pluto, that's enough to lift hazes and drive gentle cycles of frost and sublimation. As Pluto recedes again into the colder reaches of its orbit, that thin atmosphere begins to collapse, freezing back onto the surface in a quiet condensation that may take decades to complete. Scientists predict that by the late 21st century, Pluto could be nearly airless again, its blue haze gone, its sky silent. But give it a few more centuries, and the process will reverse. The same gases will reawaken, thaw, and rise once more. It's an atmosphere that breathes on the scale of millennia, an exosphere that blinks in and out of existence. Other large Kuiper belt objects seem to share versions of this rhythm. Eris, for example, is even colder and farther from the Sun, but when it swings closer during its 560-year orbit, its bright reflective surface suggests frost activity, perhaps the brief awakening of an atmosphere that spends most of its time asleep. Makemake too shows patches of volatile ices that could sublimate under sunlight, hinting that it experiences a similar cycle. These are worlds whose weather reports could be written once every few centuries and still be considered up to date. Even among smaller Kuiper belt objects, gases can sometimes escape through slow outgassing, the release of trapped volatiles from within the ice. Cosmic radiation, micrometeoroid impacts, or even weak heating from sunlight can loosen molecules of nitrogen, carbon monoxide or methane, sending them trickling into space. But with gravity so faint, these gases don't linger long. Most drift away, forming brief halos before vanishing into the solar wind. What remains momentarily is what astronomers call an exosphere, a cloud so tenuous that its molecules rarely collide, each following its own lonely trajectory until it escapes. Yet despite their fragility, these transient atmospheres can leave visible signatures. When a Kuiper belt object passes in front of a distant star, a stellar occultation, its exosphere can subtly dim or refract the starlight, revealing details about its density and composition. It's an extraordinary feat of detection, measuring something so delicate that it barely exists, using light that has travelled for years only to blink for seconds. Through these events, astronomers have detected hazes, pressure variations, and even hints of seasonal layering, all from the faintest flickers of starlight. But the Kuiper belt surprises don't stop with thin air. Some of its icy residents also wear rings, graceful, improbable bands circling worlds that seem far too small to hold them. The discovery of rings around distant objects like Haumea and Quaoar shocked scientists who had long assumed such features belonged only to the giant planets, and yet there they are, delicate hoops of dust and ice, orbiting tiny bodies under the gentlest of gravitational pulls. These rings were discovered not through telescopes directly, but again through stellar occultations. As the object passed in front of a star, astronomers noticed the starlight dimmed not once but several times, brief symmetrical flickers before and after the main event. Those twin dips could only mean one thing, something thin and circular, orbiting the body like a halo. In Haumea's case, the ring lies near its equatorial plane, and may be composed of icy debris shed from its rapid spin or a past collision. Quaoar's ring, even more puzzlingly, orbits far beyond the distance where traditional models say such material should be stable. So how do rings survive around such small worlds? The answer may lie in balance. The particles that form them are constantly being lost and replenished. Micrometeoroid impacts kick up fresh material from the surface, while some grains drift away under the pressure of sunlight. The result is a steady but delicate equilibrium, a faint shimmer that endures not because it's permanent, but because it's constantly renewed. If you could see one of these rings up close, it would likely look ghostly, more like a mist than a solid band, its particles tracing silent arcs through darkness. Together, the Kuiper Belt's rings and exospheres remind us that even in the farthest reaches of the Sun's domain, things are not as still as they seem. These distant worlds breathe, shed, and renew themselves in cycles of astonishing patience. Gases rise and fall like tides, dust dances and disperses, ices erode, condense, and sublimate again. Its planetary behaviour reduced to its most minimal form, a slow heartbeat beneath layers of frost. Each process depends on delicate balances. A little more sunlight, and the ice releases gas. A little less, and it freezes again. A tiny impact can raise a cloud of particles. A passing solar breeze can sweep it away. The gravitational fields of these objects are so weak that even small changes can send molecules flying into space. For worlds like Haumea or Make, holding on to anything as intangible as an atmosphere is a feat of cosmic restraint. And yet, fragile as they are, these features reveal an important truth. Even in the coldest corners of the solar system, nothing is entirely static. Change still happens. It just happens quietly. Where the inner planets roar with storms and eruptions, the Kuiper Belt murmurs. Its processes move on timescales that stretch human imagination. A frost that creeps across a pole in 1,000 years. A ring that brightens and fades over the span of centuries. To witness such things is to learn a different kind of patience. When astronomers describe a season on Pluto or a temporary ring around Quaoar, they're speaking in intervals that outlast civilizations. These are features so ephemeral that to human eyes they might as well be eternal. Blink, and a century passes. Wait long enough, and the sky itself changes colour. It's easy to think of the Kuiper Belt as frozen and unchanging, but the truth is subtler and more beautiful. Even here, 4.5 billion kilometres from the Sun, surfaces breathe, atmospheres flicker, and rings shimmer in silence. They are reminders that time never truly stops, only slows. The universe keeps moving, even when the motion is measured in whispers. In the Kuiper Belt, you can see that motion written across ice and shadow. A faint haze glowing in the starlight, a ring catching a glimmer of the distant sun, a molecule of nitrogen taking flight after 100 frozen centuries. These are the faintest gestures of life in a place too cold for warmth, too quiet for wind, and yet they prove that even the smallest worlds, even the loneliest orbits are never truly still. The Kuiper Belt from afar might look like a realm of quiet stillness, a vast frozen ring of worlds locked in place for eternity. And in a sense, that's true. Many of its icy residents have circled the sun in peace for more than 4 billion years, their paths so stable that not even the slow ticking of cosmic time has disturbed them. Yet beneath that serenity lies a delicate balance, a long, slow dance choreographed by gravity itself. Each object, from the tiniest pebble to Pluto-sized giants, moves to a rhythm set by the sun, the planets, and subtle forces that take eons to play out. The first step in understanding this cosmic choreography is realizing just how stable can be. For most Kuiper Belt objects, The orbits they follow today will still be recognizable billions of years from now. They may shift slightly, their shapes and tilts wobbling over time, but the sun's gravity and the orderly spacing of the planets keep them mostly safe from chaos. Think of it like a pond on a windless morning. The surface appears perfectly calm, yet beneath it, small ripples glide in quiet patterns that never quite collide. These stable regions exist because the Kuiper belt, while wide, is not random. Many objects are locked into resonances with Neptune, mathematical relationships that keep their orbits synchronized. For instance, Pluto and a whole class of objects known as Plutinos are in a 3-to-2 resonance, meaning they complete 2 orbits around the Sun for every 3 of Neptune's. This relationship prevents close encounters. When Pluto swings inward, Neptune is always elsewhere in its orbit, as though the 2 worlds have agreed never to meet. Over billions of years, this gravitational choreography has preserved Pluto's orbit from instability, allowing it to dance safely between the giants. But not all regions of the Kuiper belt are so tranquil. Where resonances overlap or interfere with one another, chaos quietly stirs. In these zones, small changes can grow over time, amplifying like the pluck of a single string that sets the whole instrument humming. An object that strays too close to such a region can find its orbit gradually stretched, tilted, or even ejected entirely. This chaos doesn't look like sudden violence. It's more like the slow diffusion of energy in a dream, where patterns blur and dissolve across the ages. Over millions or billions of years, some objects drift inward to become centaurs or comets, while others are flung outward into darkness. One of the most graceful yet subtle motions within this long-term ballet is known as the Kozai cycle, a gravitational exchange that allows inclination and eccentricity to trade places. Imagine a small Kuiper belt object orbiting at a strange tilt relative to Neptune. Over immense timescales, its orbit can oscillate. As the tilt, its inclination decreases. The shape of the orbit, its eccentricity, becomes more elongated, and vice versa. The total energy remains the same, but its form shifts, like a skater trading speed for height in a slow-motion routine. This process can make orbits breathe over eons, swelling and flattening in an almost hypnotic rhythm. The Kozai effect, named for Japanese astronomer Yoshihide Kozai, helps explain how some distant worlds maintain their peculiar paths without being thrown into chaos. It's a cosmic stabilizer of sorts, turning potential disorder into graceful oscillation. Some of the most extreme trans-Neptunian objects, those with steeply tilted or highly elongated orbits, owe their longevity to this quiet balancing act. Without it, their paths might have unravelled long ago. Yet even in this stable zone, nothing is truly static. Tiny forces, often invisible in the short term, accumulate over immense spans of time. One of these is the YORP effect, a subtle torque caused by the uneven reflection of sunlight from a rotating body's surface. When light strikes an object and is re-emitted as heat, it imparts a faint push. Over millions of years, those countless photon nudges can gradually alter a small world's spin, making it rotate faster or slower. Far from the Sun, the YORP effect is extremely weak, almost negligible, but in a realm where patience is measured in billions of years, even a whisper of force can become meaningful. A slow change in rotation can, in turn, shift how sunlight warms the surface, potentially influencing how ices sublimate or how dust settles. These are not dramatic changes, they're quiet, cumulative drifts, like watching the hour hand of a clock move only when you're not looking. Thermal effects, too, play a small but persistent role. Even at temperatures below -200 degrees Celsius, the cycle of day and night creates gentle thermal gradients. These minute expansions and contractions of surface materials can, over geological timescales, redistribute mass slightly altering an object's spin or shape. Micrometeoroid impacts, though rare, add another layer of slow change, imparting faint jolts that accumulate over eons. None of these forces are enough to shake the Kuiper Belt's stillness, but together they create a kind of cosmic breathing, an imperceptible pulse that keeps everything subtly in motion. The interplay of stability and chaos across the Kuiper Belt paints a portrait of the solar system as both orderly and unpredictable. Some regions are so stable that orbits there have persisted since the dawn of planetary formation. Others, teetering on the edges of resonance, churn with quiet unrest, sending the occasional wanderer drifting toward the inner worlds. From afar it looks peaceful. Up close, it's a masterpiece of balance, tension, and timing. Over giga-year timescales, gravitational interactions weave this stability into a kind of music, slow, soft, and continuous. Neptune's orbit hums the bass line, setting the tempo. The sun's pull defines the rhythm. And the Kuiper Belt objects move like gentle notes, sometimes harmonizing, sometimes dissonant, but always part of the same grand composition. To grasp just how stable many of these orbits are, consider this. A Kuiper Belt object in a safe resonance with Neptune might complete millions of revolutions around the Sun without any significant deviation. For something so small and distant, that's an extraordinary feat of endurance. It's as if time itself flows differently there, stretched by distance and diluted by quiet. But for every region of long-term calm, there's another where the boundaries blur. Even minor gravitational tugs from passing stars or the slow drift of the planet's orbits can, over billions of years, alter the shape of the belt. These changes are not abrupt. They unfold on scales far beyond human experience, but they remind us that stability is never absolute. Even in the most tranquil ponds, ripples eventually meet. What emerges then is a picture of the Kuiper Belt not as a frozen relic, but as an almost still pond, one where the surface seems calm, yet subtle waves glide beneath. The gravitational fields of the planets, the sun's distant warmth, the faint push of light, all these forces ripple through it endlessly. Over time they sculpt the orbits, spin the bodies, and occasionally tip one world into a new path. It's a kind of cosmic patience beyond comprehension. The Kuiper Belt doesn't shout its changes, it whispers them. Its worlds drift, tilt, and breathe with motions so slow they might as well be eternal. And yet, through those quiet ripples, the structure of the outer solar system has endured for billions of years, a testament to the resilience of order within chaos, and to the soft gravity of time itself. Far out in the cold, beyond Neptune's serene blue orbit, the Kuiper Belt holds onto a treasure older than any planet. Locked inside its ice and dust are the original ingredients from which everything we know was made: carbon, nitrogen, water, and the faint chemical hints of something more. These frozen worlds are not lifeless in the dismissive sense. They are lifeless only in the way a seed is lifeless before it finds soil. If the inner solar system was the kitchen where planets cooked up oceans and atmospheres, the Kuiper Belt is the pantry, dark, quiet, and stocked with all the right materials. When scientists first began studying comets, they quickly realized that these icy wanderers were more than just pretty tails and glowing heads of gas. Comets are fragments from the same region that birthed the Kuiper Belt, and their chemistry reads like a recipe list for life as we know it. Inside them are frozen water, carbon dioxide, ammonia, methane, and a collection of organic molecules ranging from simple alcohols to complex carbon chains. Some even carry amino acid precursors, the molecular building blocks from which proteins can form. These are not fossils of life, but rather its raw materials, preserved since the solar system's dawn. The remarkable thing is that these ingredients have remained essentially unchanged for over 4.5 billion years. The Kuiper belt is so cold, temperatures drop below minus 200 degrees Celsius, that chemical reactions nearly stop. Molecules that would quickly degrade or combine closer to the Sun are instead frozen in time, waiting. Radiation from distant starlight and cosmic rays slowly modifies their surfaces, creating tholins, reddish, tar-like substances rich in organic complexity. Over billions of years, this cosmic chemistry writes new patterns in the ice, layering each world with potential. It's not unreasonable to think of these distant bodies as chemical archives. Every surface, every grain of ice preserves information about the conditions that existed when the solar system was still a swirling disk of gas and dust. By studying the composition of Kuiper belt objects and their relatives, scientists are essentially reading the solar system's oldest notebook, and what that notebook says, quietly and clearly, is that organic chemistry didn't wait for Earth. It began long before Earth even existed. The delivery of these frozen ingredients to the inner planets likely came through a mix of slow diffusion and occasional drama, when gravitational interaction sent comets inward, especially during the early late heavy bombardment period about 4 billion years ago. They acted as couriers, sprinkling their volatile cargo onto young worlds. Each impact released water, carbon, and complex organics into the warm light of the inner solar system. Over countless collisions, that delivery service may have stocked Earth's early oceans with the raw materials needed for biology to begin. It's an elegant thought that the origins of life on Earth were written in ice at the solar system's edge. Every droplet of water, every strand of DNA may trace its ancestry to the chemistry of comets and Kuiper belt dust. Even today, when we sample comets directly, the resemblance between their chemistry and life's building blocks is uncanny. The European Space Agency's Rosetta mission to Comet 67P found amino acid precursors, while NASA's Stardust mission captured complex organic compounds from Comet Wild 2. These findings reinforce a simple, beautiful idea. Life's ingredients are not unique to Earth. They are written into the blueprint of the cosmos, but it's important to keep the speculation grounded. The Kuiper belt isn't hiding microorganisms or frozen fossils of alien cells. The environment is far too cold and the radiation too harsh for anything alive to persist in the biological sense. What it offers instead is chemistry, the quiet, persistent kind that doesn't mind waiting a few billion years for the right opportunity. In those long spans of stillness, molecules bond, split, and reform in patterns that hint at future possibilities. The significance of that chemistry cannot be overstated. If the Kuiper belt and its cometary emissaries carried prebiotic materials across the solar system, then life on Earth, and perhaps elsewhere, didn't arise from a single lucky location, but from a shared inheritance of cosmic materials. It suggests that biology may be a natural extension of planetary chemistry, not a miraculous exception. Every world that receives a dusting of this material gains a small chance at transformation. The Kuiper belt's contribution to that story is not limited to its comets. The slow erosion of its surfaces by micrometeoroids and solar radiation releases fine dust that drifts sunward, joining the interplanetary medium. Over vast timescales, that dust can be swept inward, adding trace amounts of carbon-rich material to other worlds. In this way, the belt continues to feed the inner solar system, a steady drizzle of chemistry that connects even the most distant regions. Each grain of that dust carries within it a fragment of possibility. It may contain water ice laced with organic residue, or tiny silicate cores wrapped in frozen carbon compounds. If such grains land on a planet with warmth and liquid water, the chemistry locked inside them can awaken, interacting with the local environment, It's a quiet chain reaction linking distance and destiny, from a frozen molecule in the dark to the spark of biology in the light. And while we have not yet sampled a Kuiper belt object directly, what we've learned from their closer cousins, comets and centaurs, strongly supports the idea that the belt is a vast reservoir of prebiotic material. Even the reddish colours of many of its surfaces speak to organic richness. Each hue, each spectral signature whispers of methanol, ammonia and hydrocarbons frozen together in ancient companionship. These are the same ingredients that, when given energy and time, can form sugars, amino acids, and other molecules essential for life. When you step back and look at it in full, the story feels deeply optimistic. Life, or at least the chemistry that makes life possible, seems to be woven into the very fabric of planetary formation. The Kuiper belt doesn't need oceans or sunlight to play its role, it simply has to wait. It keeps its ingredients cold, clean, and preserved, ready for the day they might find a warmer home. In that sense, it's less a graveyard of ice, and more a cosmic pantry stocked with potential. Every comet that streaks through the night sky is a reminder of this connection. When you watch one glow against the stars, you're seeing material older than any mountain or ocean on Earth. Material that helped make both. Each shimmering tail is a trail of molecules that have survived since before the planets took shape. They are the universe's way of keeping the spark alive, even in the deepest cold. Cold shelves hold warm possibilities. It's a quiet truth that captures the spirit of the Kuiper belt perfectly. Out there, in the dim light beyond Neptune, chemistry waits patiently, unfrozen in purpose if not in form. The same molecules that once drifted through the solar nebula still linger there, unchanged, dreaming of the right conditions to begin again. Perhaps someday, on another world under another sun, those ingredients will stir once more, and life, in its endless curiosity, will wake up to find itself among the stars. The Kuiper belt may lie in shadow, but the tools we use to study it are growing brighter with every passing year. For most of human history, that distant frontier was invisible, a dark ring of mystery beyond Neptune's faint orbit. Even now, its worlds are dim enough to hide in plain sight. Yet with each new telescope, each carefully planned mission, that darkness thins a little. Slowly, methodically, astronomers are learning to read the belt's quiet script line by frozen line. The next generation of telescopes promises to transform our understanding of this faraway region. Large-scale surveys from Earth will soon map the Kuiper belt with unprecedented precision, revealing thousands of new objects too faint to detect before. Instead of discovering one or two worlds at a time, these observatories will gather them by the hundreds, tracking their motion across the sky with exquisite accuracy. Each faint dot of light adds a new data point, a clue about how the solar system's outskirts are shaped, and how its ancient architecture evolved. By refining orbits, astronomers can untangle the belt's complex structure, tracing families, resonances, and populations that were once blurred together. Small variations in brightness reveal rotation rates and surface compositions. Subtle changes in position help measure gravitational interactions. Piece by piece, the static map of the outer solar system becomes a living model, full of movement and meaning. The cold frontier begins to feel less like an edge and more like a community of worlds, each one turning quietly in its lane. These ground-based surveys will pair beautifully with space telescopes designed to sense what visible light can't show. Many Kuiper belt objects are so cold that they barely shine at all in reflected sunlight, but they do emit faint thermal radiation, tiny glimmers of warmth that can reveal their true sizes and compositions. By measuring this thermal emission, astronomers can tell whether an object's faintness is due to small size or dark surface material. The difference may sound minor, but it helps distinguish between an asteroid-like body of rock and a fluffier, ice-rich world. Spectroscopy too will play a vital role. By splitting light into its constituent colours, telescopes can identify specific chemicals frozen on these distant surfaces. Methane, water ice, ammonia, and complex organics each leave distinctive fingerprints in the spectrum. These data allow scientists to see how chemistry varies across the belt, why some regions are bright and neutral, while others glow a deep red. It's a kind of remote archaeology, reading molecular clues written billions of years ago. Future space telescopes will make this even clearer. Instruments orbiting far from Earth's atmosphere will detect subtle differences in composition and temperature that ground-based observatories simply can't see. With high-resolution infrared vision, they'll be able to study how radiation, sunlight and cosmic rays slowly modify the ices over time. We'll be able to tell whether one Kuiper belt object's surface is young and freshly exposed, or ancient and darkened by eons of space weathering. In a way, these telescopes will act like time machines, peering through the layers of ice to glimpse what the early solar system was really made of. But telescopes, no matter how powerful, can only do so much from afar. To truly understand the Kuiper belt, we'll eventually need to return. This time, not just to fly past one world, but to visit several. After the success of New Horizons, mission planners have begun imagining spacecraft designed to tour multiple Kuiper belt objects. These missions would not race through the region, but linger, drifting from target to target over decades. Each encounter would reveal a new kind of terrain, a new flavour of ice, a new clue about the processes that shape the belt. A touring spacecraft could study how different Kuiper belt objects vary in colour, density and geology, how some are smooth while others are jagged, how some hold rings or moons while others travel alone. It could look for thin exospheres or faint particle streams that telescopes can't see, and measure the composition of surface ices directly. With careful design, such a mission could rewrite our understanding of how the solar system's outer edges evolved, and how it continues to change in the deep cold. Even more ambitious is the idea of a sample return mission, sending a probe to collect a fragment of a Kuiper belt object and bring it back to Earth. Such a feat is still decades away, perhaps more, and would require extraordinary patience and precision. But the rewards would be immense. Holding a piece of pristine Kuiper belt ice in a laboratory would give scientists direct access to the solar system's oldest chemistry, unaltered by heat or pressure. It would be like studying the ink on the first page of the universe's diary. In the meantime, astronomers continue to push the limits of what can be seen from afar. Occultation networks, groups of observers scattered across the globe, are now watching for the brief moments when distant stars blink behind a Kuiper belt object. These flickers reveal sizes, shapes, and even the presence of rings or atmospheres. Combined with data from new surveys and space telescopes, they form a mosaic of precision, filling in details that no single instrument could capture alone. The future of Kuiper belt exploration will not be a sudden burst of discovery, but a steady illumination. Each new observation adds a little more light to a region once thought impenetrable. A faint object that today appears as a single pixel may, a few decades from now, be mapped in colour and texture, its orbit known to within a fraction of a kilometre. Slowly, the belt is emerging from anonymity. Its residents are no longer nameless dots, but worlds with stories, each a survivor of creation's earliest chapter. The beauty of this process is in its pace. Studying the Kuiper belt demands the same patience it took to form it. Light from those distant ices takes 6 hours to reach us, and knowledge about them comes almost as slowly. But that's fitting. This region has waited billions of years to be understood. It doesn't mind taking its time. When you picture the future of Kuiper belt exploration, Imagine a long winter night dotted with lanterns. Each new telescope, each mission, is one more light in the darkness, small but steady, revealing what was once invisible. The belt itself remains cold, silent and unhurried, but above it, our understanding burns a little brighter. One by one, those lanterns illuminate the frozen frontier, reminding us that even the farthest shadows yield to curiosity. In time, the Kuiper belt's winter will not seem dark at all, but softly aglow with discovery. At first glance, the Kuiper belt seems endless, an icy plain stretching outward from Neptune into the dark, fading gently into interstellar space. But look closely, and you'll find that the belt doesn't continue forever. Somewhere around 50 astronomical units from the Sun, just beyond the comfortable middle of this frozen domain, the population of known objects drops sharply. It's as though the solar system's backyard ends abruptly, the pebbles and snowballs giving way to emptiness. Astronomers call this mysterious drop-off the Kuiper cliff. The name captures the feeling perfectly. It's not a physical cliff you could stand on, of course, but a statistical one. A sudden change in the number of objects we see. Inside 50 astronomical units, telescopes find Kuiper belt objects aplenty. Dwarf planets, binaries, scattered worlds, and small icy fragments. But past that boundary, detections plummet. For years, scientists wondered if this apparent edge was merely an illusion caused by faintness. Perhaps the objects beyond were simply too small or too dark to spot. But even after decades of improved surveys, the cliff remains stubbornly steep. Something real is happening there. The simplest explanation might be that the Kuiper belt simply ran out of building material. In the early solar system, when the Sun was still wrapped in its protoplanetary disk of gas and dust, temperature and density dropped with distance. Farther from the Sun, there was less solid matter for planets or planetesimals to form from. Beyond about 50 astronomical units, the density of material may have fallen below a critical threshold, leaving the region sparsely populated. It's a natural limit, the place where the solar system's construction site simply closed for the day. But there are other more dynamic possibilities. One idea involves the slow outward migration of Neptune, the great sculptor of the Kuiper belt. As Neptune drifted away from the Sun, its gravity would have tugged and shuffled nearby icy bodies, trapping some in resonances and flinging others into chaotic orbits. This process could have cleared out much of the belt's outer region, leaving behind a sharp edge where Neptune's gravitational influence eventually weakened. In this scenario, the cliff is a fossil scar of planetary motion, a frozen memory of the time when the giant planets rearranged themselves. Another possibility lies in the gentle tug of unseen forces or distant objects. Some astronomers have speculated that a large, undiscovered planet, often called Planet 9, might be shaping the outer belt structure from afar. Its gravitational reach, though faint, could shepherd or eject small objects beyond 50 astronomical units, creating an apparent boundary. So far, no such planet has been confirmed, and the evidence remains circumstantial, but the idea persists because it neatly explains certain orbital quirks seen in the most distant trans-Neptunian objects. Of course, part of the mystery could still be observational. The farther out an object is, the fainter and slower it appears. Even with powerful telescopes, a small Kuiper belt body beyond 50 astronomical units reflects only a whisper of sunlight. Its movement across the sky is so sluggish that it can easily blend with background stars. Detecting such faint motion requires patience and perfect timing, years of careful, repeated observation. It's entirely possible that many objects simply escape notice, hiding in the gaps between data frames. The Kuiper cliff then might not be quite as sheer as it appears. It could be more of a foggy horizon than a sharp drop. Still, the evidence points to something more than just hidden faintness. The total mass of the Kuiper belt, even accounting for undiscovered bodies, is far less than early models predicted. Some calculations suggest that the region holds only about 0.1% of Earth's mass. To have formed the dwarf planets and numerous smaller bodies we see today, the belt must once have been hundreds of times more massive. The Kuiper cliff may mark where that material was either never present or where it was stripped away long ago. Understanding where and why the belt ends is more than a matter of curiosity. The edge holds clues to how the solar system itself was assembled and how it interacts with the wider galaxy. If the belt truly ends around 50 astronomical units, that boundary could represent a dividing line between the orderly solar system we know and the far more distant Oort cloud, a vast, diffuse sphere of icy fragments extending tens of thousands of astronomical units outward. In this way, the Kuiper belt might serve as a kind of shoreline, one side solid ground, the other an open ocean of comets and drifting debris. Imagine walking along that shoreline. Behind you stretch familiar dunes of ice, Pluto, Haumea, Makemake, each gleaming softly in the faint sunlight. Ahead lies a smooth, untouched expanse where footprints fade into nothing. That's the Kuiper cliff, the place where the pattern ends, where the last grains of planetary formation give way to silence. Beyond it, the density of objects drops so low that the next neighbours may be light years apart. To scientists, that fading frontier is as meaningful as the discoveries closer in. Edges define systems. They tell us where the rules change. The Kuiper cliff may hold answers to why the early solar system formed the way it did, and perhaps why other planetary systems look different. Observations of disks around young stars show similar outer edges where planet formation seems to stop. The processes that sculpted our own belt might be universal, repeating in countless other systems scattered across the galaxy. As new telescopes and surveys extend their reach, astronomers continue to push beyond the cliff, searching for stragglers and secrets. Each discovery of a far-flung object, whether it orbits at 60 or even 100 astronomical units, helps redraw the faint outer border of the solar system. Some of these bodies may act as intermediaries between the Kuiper belt and the more distant Oort cloud, bridging two realms of ice separated by an ocean of emptiness. The Kuiper cliff remains one of the most intriguing puzzles of planetary science, a place where statistics and science meet. It's neither abrupt nor absolute, but it marks a transition that feels poetic nonetheless. Here, the music of the solar system quiets to a hum. The dance of resonances and collisions slows until it is almost still. What lies beyond may not be entirely empty, but it is quiet enough to feel infinite. In the end, the Kuiper cliff reminds us that even boundaries can be beautiful. It is the edge of the known, the place where light thins and distance begins to win. And like any shoreline at dusk, it invites curiosity rather than finality. Somewhere beyond that soft horizon, more worlds may wait, tiny, frozen, and patient as ever, guarding the last traces of the solar system's story, where footprints fade into untouched snow. Every so often, a discovery reminds astronomers that the solar system still holds secrets it isn't quite ready to explain. In the quiet outskirts beyond Neptune, a handful of icy bodies seem to follow orbits that don't fit the usual rules. Their paths are tilted, elongated, and most mysteriously detached. They never come close enough to the giant planets to have been shaped by them, yet they still move in harmony with the rest of the solar system. These detached worlds drift at the edge of the known, distant and aloof, as if keeping a respectful distance from the chaos closer in. The most famous of these is Sedna, discovered in 2003. Its orbit carries it from a perihelion, or closest point to the Sun, of about 76 astronomical units. all the way out to nearly 1,000. That's a journey so vast that Sedna takes over 11,000 years to complete a single orbit. It spends almost all that time wandering in darkness, far beyond the Kuiper belt's busy inner regions. Other objects, like 2012 VP113 and several newly identified bodies, share similarly stretched high perihelion orbits. Together, they form a small but intriguing population that refuses to play by the same gravitational rules as everyone else. The puzzle is simple to describe but difficult to solve. If Neptune can't reach them with its gravity, what shaped their paths? To send an object into such an elongated orbit, some significant event or influence must have nudged it long ago. Yet none of the known planets can account for it. That mystery has led scientists to propose several possibilities, some grounded, some exotic, all fascinating in their own quiet way. One explanation looks back to the solar system's earliest days, when the Sun was not alone. Like most stars, it was born in a stellar nursery, an open cluster filled with hundreds or even thousands of sibling stars. In those crowded beginnings, a passing star could have come close enough to tug at the outer edges of the Sun's disk. A gravitational brush, gentle by cosmic standards but mighty in effect, might have pulled a few planetesimals into elongated orbits before drifting away forever. Over billions of years the rest of the cluster dispersed, leaving only these objects behind as evidence of that ancient encounter. In this view, Sedna and its companions are souvenirs from the solar system's childhood, a faint memory of the time when our star had neighbours. Another possibility focuses on the complex ballet of resonances within the Kuiper belt itself. Even if Neptune doesn't directly scatter these bodies, its subtle gravitational rhythms could interact over long timescales to nudge some objects outward, lifting their perihelia higher and higher through a process called secular resonance. It's not as dramatic as a planetary kick or a passing star's shove. It's more like a slow accumulation of gentle tugs that, given enough time, reshape an orbit entirely. Over hundreds of millions of years, an object could drift from the Kuiper belt's outer rim into a detached orbit without any mysterious planet required. Still, one hypothesis continues to capture both professional and public curiosity: the possibility of an undiscovered massive world lurking far beyond Neptune. Often nicknamed Planet 9, this hypothetical object is thought to be several times more massive than Earth, tracing a distant elliptical orbit that could take thousands of years to complete. If it exists, its gravity could shepherd smaller bodies into aligned, clustered paths, explaining why so many detached objects seem to point in similar directions. The idea is not new. Astronomers have been searching for a missing planet beyond Neptune for more than a century. From Percival Lowell's early calculations in the 1900s to the modern statistical models of today. What makes the current theory different is that it's driven by observed patterns rather than wishful thinking. When multiple detached objects share certain orbital alignments, similar directions of perihelion and inclination, it hints at a common cause, and the simplest explanation, mathematically speaking, might be a distant, unseen perturber. Yet caution is the watchword here. The evidence is still statistical and the sample size small. Observational bias plays a large role. Telescopes tend to find objects in regions of the sky they can observe most often, which can create patterns where none truly exist. As more detached worlds are discovered and their orbits precisely measured, the supposed clustering might fade into randomness. Until then, Planet 9 remains an intriguing possibility, but not a certainty. What's remarkable is that this mystery doesn't need melodrama to be captivating. Whether there's a hidden planet or not, the detached objects themselves are fascinating enough. Each one represents a remnant from the solar system's early rearrangement, a time when giant planets shifted, disks dissipated, and countless smaller bodies were scattered into exile. These survivors have held their distant, lonely orbits ever since, carrying with them information about those forgotten centuries. New sky surveys are already expanding the catalogue of known trans-Neptunian objects, and with every addition, the picture grows clearer. The next few years will likely double or triple the number of detached bodies known. Once that happens, astronomers can compare their orbital orientations statistically, separating coincidence from correlation. If the alignments persist even after accounting for biases, the case for a massive perturber will strengthen. If they fade, simpler explanations, stellar encounters, or resonant processes will prevail. In that sense, the mystery may be solved not by a telescope but by mathematics. Careful modelling and simulation can reproduce the solar system's dynamics across billions of years, testing which scenarios produce detached orbits like Sedna's. Already, these digital experiments have shown that multiple explanations can create similar patterns. The difference lies in the details, the spacing of perihelia, the tilt of orbital planes, the slow precession of long axes over time. Somewhere within those subtleties lies the truth. Meanwhile, the search for Planet 9 continues quietly. Observatories around the world and in orbit are combing the sky for faint, slow-moving specks that could match the predicted parameters. It's a painstaking effort. If such a planet exists, it would be hundreds of times farther from the Sun than Earth, reflecting sunlight so weakly that it would appear dimmer than the faintest stars visible through binoculars. Finding it will require years of data, meticulous comparison, and a fair amount of patience. But astronomers are used to that. After all, the universe rarely reveals its secrets in a hurry. Detached worlds remind us that not every mystery needs immediate resolution. Their existence invites curiosity rather than certainty, and that's part of their beauty. They drift through orbits so vast that a single journey takes longer than all of recorded human history. For now, we can only watch their slow arcs and wonder what unseen forces placed them there. Whether shaped by a passing star, a distant resonance, or a hidden planet, these objects serve as quiet witnesses to the solar system's outer story. They hint at a time of movement and chaos that has long since subsided into calm. Their stillness now is deceptive. It conceals the memory of ancient motion, like ripples frozen in ice. In the deep dark beyond the Kuiper belt, they glide untouched, patient and persistent. And perhaps that's the lesson they offer. Some questions, like the orbits of these distant worlds, take time to complete their cycles. In the end, whether or not Planet 9 is ever found, the search itself, slow, methodical, and full of wonder, is a reminder that mystery is not an obstacle in science, it's an invitation. If the solar system were a kitchen, then its two great belts would be the different aisles of its pantry, both stocked with ancient ingredients, but preserved under entirely different conditions. The asteroid belt circling between Mars and Jupiter is warm, rocky and metallic, a dusty cupboard where time has baked and cracked its contents. The Kuiper belt far beyond Neptune is the deep freezer, a silent isle of ice and organics kept perfectly chilled for over 4 billion years. Both are leftovers from the same cosmic recipe, but their flavours couldn't be more different. Let's start with composition, the foundation of their personalities. The asteroid belt's members are built mostly from rock, silicate minerals, and metal. Many are thought to be fragments of would-be planets that never finished forming, their material scattered and stirred by Jupiter's overwhelming gravity. Some, like the M-type asteroids, even contain significant amounts of nickel and iron, the same alloys that make up Earth's core. Others, the carbonaceous C-types, are darker, primitive, and rich in carbon compounds. Together, they represent a cross-section of what the inner solar system was made from, hot, dry, and hard. In contrast, the Kuiper belt is a place of frost and faint sunlight. Its inhabitants are built from a mix of rock and volatile ices, water, methane, ammonia, nitrogen, and carbon monoxide, all frozen solid in the deep cold. Many also carry complex organics known as tholins, formed when radiation slowly alters surface ices into reddish-brown polymers. These substances give many Kuiper belt objects their warm hues, even though they live in a place where warmth itself barely exists. If asteroids are like baked stones from a sunlit oven, Kuiper belt objects are more like frozen confections that have never known heat. Temperature shapes everything about them. In the inner solar system, sunlight is strong enough to strip away volatile materials. Any ice once present in the asteroid belt has long since sublimated into space, leaving behind rock and metal cores. In the Kuiper belt, sunlight is more of a gentle suggestion than a presence. The temperatures hover around -200 degrees Celsius, cold enough that even nitrogen and methane can form frost. At those temperatures, ices behave like rock, and erosion moves at the pace of centuries. A collision that would shatter a warm asteroid might leave only a soft bruise on a frozen Kuiper belt world. Their contrasting environments have sculpted very different histories. The asteroid belt's evolution has been turbulent. Early in the solar system's life, Jupiter's gravity disrupted the formation of any large planet between Mars and itself. Instead of one world, thousands of smaller ones emerged, only to be scattered, shattered, and stirred by gravitational resonances. Over billions of years, collisions ground down many of these bodies into smaller fragments, producing the dust that still drifts between them today. The belt we see now is only a shadow of what it once was, perhaps just a few percent of its original mass. The Kuiper belt, by comparison, had a gentler upbringing. Neptune's migration outward reshaped its structure but didn't pulverize it to the same extent. Its orbits are slower, collisions rarer, and impacts far less energetic. That's why many Kuiper belt objects remain pristine, their surfaces preserving the chemistry and structure of the early solar system almost unchanged. They are time capsules of planetary beginnings, where ancient ices still whisper the story of formation. In the asteroid belt, collisions are acts of violence. In the Kuiper belt, they're more like slow-motion embraces. When asteroids collide, they strike at several kilometers per second, releasing energy enough to melt and vaporize rock. When Kuiper belt objects meet, their relative velocities are often only a few hundred meters per second. Instead of shattering, they may merge or gently fragment, producing contact binaries like Arakoth. Two worlds that lean together and never parted. It's a dance dictated by distance. The farther from the sun, the slower everything moves. Even the colour of these regions tells part of the story. Most asteroids are grey to charcoal black, their surfaces weathered by sunlight and micrometeorite impacts. The absence of volatile ices leaves little room for chemical variety. The Kuiper belt, on the other hand, displays a surprising palette: reds, browns, and even subtle blues. These hues come from surface chemistry. Tholins forming in the uppermost layers of ice as cosmic rays break and rebuild molecules over billions of years. It's as if the asteroid belt has been sun-bleached, while the Kuiper belt has been slow-baked under a faint ultraviolet glow. Dynamically, the two belts tell complementary tales of planetary influence. Jupiter is the undisputed architect of the asteroid belt. Its immense gravity stirred the region early on, clearing gaps known as Kirkwood resonances and ensuring that no large planet could ever assemble there. The asteroid belt became a place of perpetual agitation. Its members constantly nudged, reoriented, and occasionally flung toward the inner planets. Many meteorites that fall to Earth today began their lives in those unstable corridors, ejected by Jupiter's invisible hand. In the outer solar system, Neptune plays a similar but subtler role. Its migration through the primordial disk sculpted the Kuiper belt structure, trapping some objects in orbital resonances like Pluto's 3-2 lockstep, while scattering others into elongated orbits. Yet because distances are so vast and gravitational pull so faint, Neptune's shaping influence feels more like choreography than collision. The result is a beautifully ordered chaos, clusters of objects moving in harmony across millions of years. The two belts also differ in how their surfaces record time. The asteroid belt surfaces are ancient but scarred, cratered, pitted, and often covered with regolith ground fine by repeated impacts. Every asteroid carries the signature of countless collisions. Some have even been broken apart and reassembled into rubble piles, loosely held together by gravity. The Kuiper belt surfaces, though also old, often appear smoother. The lower frequency and energy of impact mean fewer scars, and radiation-driven chemistry continually refreshes their outer layers. The difference is striking. One region tells a story written in craters, the other in colour. Despite these contrasts, the asteroid and Kuiper belts are siblings, born of the same solar system but shaped by their neighbourhoods. Both contain the raw materials from which planets were built: rock, metal, and ice, preserved under very different conditions. They remind us that distance from the Sun doesn't just change temperature, it changes the entire rhythm of cosmic evolution. Their comparison also sheds light on the diversity of planetary systems elsewhere. Observations of other stars show debris disks glowing in infrared light, belts of dust and ice not unlike our own. Some appear asteroid-like, warm and compact, others Kuiper-like, vast and frigid. By studying both of our belts, astronomers can decode how planets form, migrate, and interact in those distant systems. Our solar system, it turns out, may be typical in its variety. If you could stroll through the solar system's pantry, you'd find that both belts hold traces of the same ingredients: silicates, metals, water, carbon compounds, but arranged in different proportions and temperatures. The inner aisle is lined with scorched pebbles and metallic crumbs, the outer with frost and frozen organics. Both tell the same origin story in different dialects. The asteroid belt speaks of heat and disruption, of worlds that tried and failed to grow. The Kuiper belt whispers of stillness and preservation, of chemistry that waited patiently for billions of years. Together they form a portrait of the solar system's complexity, not chaos but contrast. Two shelves in the same cosmic kitchen, one warmed by the sun's steady flame, the other cooled by eternal night. And perhaps that's the most elegant truth of all. The asteroid belt shows what happens when planetary ingredients are stirred too vigorously. The Kuiper belt shows what happens when they're left to rest. Both are essential parts of the same story, the tale of how planets, and maybe even life itself, were baked from the same dough but in very different ovens.